Hi everyone, welcome to this RAS specialty discussion meeting. I'm Matteo Fossati from University of Milano Bicocca and I'll be chairing this session. So according to the program, we start with an introduction from Emma Lofthouse on behalf of the SOC and a few announcements that should make our interaction, although it's only virtual, very interesting and focused on excellent science. So without further ado, I'll leave the floor to Emma, and I wish everyone a very productive meeting.
Brilliant. Thank you, Matteo. Firstly, hi everyone. As Matteo says, I'm Emma. I'm the one who's probably been emailing quite a few of you over the last couple of weeks. Apologies if there's a bit of confusion with the start time. I know some people seem to think we started at 10, but we are starting now at 10:30. And Matteo, Michele and I, we decided to kind of organise this meeting, both to kind of share our science and all the interesting things we're doing, but also to kind of take a step back, maybe be a little controversial, and to kind of assess how we're doing as a community and what kind of progress we've been making. So I was thinking a bit about this week and thinking about the amount of papers we're making. And I found it quite interesting just to have a quick look at ADS and just looking at the number of papers that we've got. So these, if I just put some random words in, the first ones that came up to my head, of course, we all know that over time, we're producing more and more papers every year. And you can see that in some things. So if you look at all the abstracts we have the word metallicity in them, for example, we do see more over time. But if we compare this to the number we see with the phrase CGN, actually in the last 10 years, the rate at which this, the use of this phrase has grown far surpassed any of the other phrases I checked. So the amount of work that's happening in this community is rapidly increasing. And I'm sure many of us are familiar with the reasons for this. So for example, this is a kind of very familiar picture. I won't be surprised if we see this again a couple of times during the later talks. And this represents the kind of idea of this large, complex, multi-phase medium which surrounds galaxies. So everything between the galaxy and kind of one Virgo radius we're referring to as the Cgn, or the circumgalactic medium. And there's lots of reasons we study this. Familiar arguments, things like the fact that a large fraction of the baryons in the universe are contained within this Cgn, this kind of halo of gas, rather than in the galaxies themselves. The idea that this Cgn is a kind of reservoir for star formation. So if we want to kind of understand how galaxies form stars and how they grow over time, we need to understand where they get that fuel from. And where they get fuel from is this gas in the Cgn. So not only is this kind of fueling the growth of galaxies, but also it can kind of act as a kind of it regulates the growth of galaxies over time. And as well as this kind of a greeting gas that it shows, we also see these large-scale outflows. And so arguments such as the fact that a large fraction of the metallicity, the metals we see in the universe are actually contained in the Cgn as a result of these kind of large-scale outflows, be that kind of from AGN or from stellar winds. So there's lots of reasons to study this area, and it's clear that a lot of us kind of are studying this area. But is this actually fulfilling its promise? Is this kind of idea of studying Cgn actually helping us to answer the questions which are outstanding in galaxy evolution? So as you probably see, this is a discussion meeting rather than kind of a traditional conference. And as a result, we want to not just hear from the speakers who are talking, but also to hear from the wider communities, to hear from all of you who are online. And so we thought we'd do a bit of polling. So everyone who's watching, you can either go to this website, just type in ahaslides.com/RASCGN, or you can use the QR code here, which I'll leave up for a bit. And if you go to this website, you should see this question: is the study of the Cgn fulfilling its promise of revealing the processes that drive galaxy evolution? And you can answer either yes, in which case, fantastic, we can all kind of sit back and relax and not worry. No, maybe we need to do a bit more work. or maybe. Or if you're not sure, there's an option for that. So please everyone vote. And while you're all doing that, I'm just going to use a couple of minutes to make some of the admin announcements. So we're starting at 10:30. We're going to talk for about 2 hours. We've got 8 talks after I've finished in a second. And we'll go through to about 1:30 UK time, at which point we'll give you an hour's break. So lunch, dinner, whatever time it is where you are. And then we're going to come back for another 2 hours of talks. And then we're going to have a discussion section at the end. So it'll be interesting. We might look at a few more polls, but also be good to hear from kind of everyone who's in the audience. We finish at bang on 3:30. Straight after we have the RAS ordinary meeting, which is kind of general admission. So if you're interested, please feel free to join that too. Now, okay, so during the talks, as you'll probably tell, there's a lot of you attendees, but we can't see you. That's because we have panelists and we have attendees. So for the speakers, when it's your turn to talk, we will be sure to promote you, it's called, to a panelist, and that will allow you, of course, to talk, which is quite important, but also to be able to share your slides. For everyone else, if you're interested in asking a question, please either put it in the chat feature. So this is kind of, if you hover at the bottom of your screen, you get a little chat speech box. All the panelists, so including the current speaker, will be able to see that. We will then ask you, we'll then unmute people who can then ask a question in person. Or if you have like a comment to make or it's too long to write down, you can also use the raise hand feature. So that should work. So if I stop sharing this now, let's have a look at how many people have voted. Okay. So we've got quite a few. So if I quickly share my screen again. Okay, so it's quite an interesting split. So we've got about a quarter of us think we're all completely sorted, or we're making progress. So which is good for us who work in this field. We're actually doing something productive. Again, a quarter don't know, which is a good reason to be here today. And then there's a bit of a split. So it'll be interesting. We're going to poll this again towards the end and see if we've got any changes. I can see that we've got 29 votes. So I'll leave this link open. If you go throughout the day, if you go to ahaslides.com/RASCGN, and we'll be using the same link later. You can keep voting. And I think on that note, it's probably a good time to step into our talks. So if I stop sharing.
Thank you, Emma. Now we have an invited talk from Joop Shea. Just promote Joop to panelist. So now you should be able to use the camera. Hi, Joop. Over to you. You should be able to share the screen. I'll give you a 5-minute warning if you wish.
Okay. Can you see my cursor?
Yes.
Okay. Good. Okay. So the circumgalactic medium. Here's a picture of the intergalactic medium and the cosmic web with Eagle, and underneath it, I've put a picture of the Muse integral field spectrograph. So I thought it'd be good to talk a little bit first about the questions that come up to me when I think about the circumgalactic medium. And I think actually the exciting thing about the circumgalactic medium is that there are so many questions. I have more questions about that than about galaxies, for example. So here's the questions I put up since I'm the first speaker. Just take a step back. So what are the questions? Well, how does the circumgalactic gas affect galaxy formation? And another one that I'm very interested in, how does it affect observational cosmology? I'll show a slide on that in a bit. How much mass is there? How much metal is there? How does the answer depend on galaxy mass, redshift, and on the gas temperature? What phases do we have? How much mass in each phase? What are the kinematics? Is it inflowing, outflowing? How can we measure this? Do the kinematics depend on the gas phase or metallicity? Is it rotating? How much turbulence is there? Where did the circumgalactic gas come from? Does it come all from the outside of the halo, or does a lot of it go through the galaxy before it gets into the circumgalactic medium again? What are the roles of magnetic pressure, cosmic rays? What about, if you're interested in the ionization conditions, what about radiation sources, local ones that may, like AGN, go on and off? What about the small scale structure? That's been a hot topic lately. How much of this small scale structure is there? How small does it get? And questions that are less often addressed. Do we care? Does it matter for galaxy formation, or does it matter for the interpretation of observations? Well, we have a lot of new information coming. I think the circumgalactic medium is a thriving subject because it's, like all of astronomy, data driven, and there's a lot of new data coming in, and that will increase also in the near future. Traditionally, absorption lines were the main way to study circumgalactic medium, but even within absorption lines, there's been a lot of changes. It's not just quasars as background sources anymore, but also gamma ray bursts, and galaxies are getting more important as we're getting bigger telescopes as background sources. It's no longer just the optical. There's a lot of work in the UV. X-ray is getting important, 21 centimeter. And the most important change, I think, in the last couple of years is that we've been able to make a much better connection between the gas in the intergalactic medium and the galaxies by using galaxy surveys, including integral field spectrographs like Muse. And also, we've been making a connection with the orientation of the galaxies, for example, for which HST observations are very important. And the Sloan surveys played a big role in getting very large samples of galaxies to correlate with. Emission is now also important, thanks mainly to integral field spectrographs. Recently, we also have FRBs that give us dispersion measures, a measure of the electron density. The electron pressure is now accessible using the Sunyaev-Zeldovich effect, and that's going to be very exciting in the near future with the Simons Observatory coming online. X-ray emission has always been there for the clusters, for the massive objects, but with eROSITA, we can have a much bigger sample and even go to some galaxies if they're nearby enough. And then a little bit further down the line, but not very far still, the kinematics and the spectroscopy is getting important with CRISM, and then later with Athena, XIFU, integral field spectrograph. 21 centimeter, also always been there, but it's really, there's a lot of new instruments that came online, and the SKA will be the main one, of course. In groups and clusters of galaxies, we can now also see other components of other phases in low frequency radio emission. And something that you may not think about, but gravitational lensing will soon be important too. Euclid and the Rubin Observatory have enough sensitivity to actually measure the mass of the circumgalactic medium if you also have access to the stellar light, for example. So that, and a model. So in combination with a model, we should be able to distinguish the dark matter, for which we know roughly the profile, and the gas. Okay, so the theory side, a lot of developments there as well. I've divided it into three categories: the large-scale hydrodynamical simulations of representative volumes. The new developments there have been, for example, refining on the CGN, which is gives you much more resolution where you want it. There's also been a lot of work on idealized simulations where you do, for example, cloud-wind interactions, or you set up a hydrostatic halo in which you can control the circumstances, let other galaxies accrete or study jets or whatever. More physics has gone in. More higher resolution also means more physics because you resolve more of the physics. But also we've been doing radiative transfer, non-equilibrium chemistry. There's been a lot of work on MHD, cosmic rays, and turbulence, even on scales that is not directly resolved. So there's a lot of very exciting developments and a lot of big questions in the CGN sphere. Here's just an illustration for those of you who need to write proposals and justify your existence to non-CGM people. If you're interested in convincing cosmologists, you can tell them that the CGM is actually very important for that. And that is illustrated here. What is shown on the y-axis is the relative difference in the power spectrum between a dark matter only and a hydrodynamical simulation as a function of the gas fraction in 10 to the 14 solar mass halos. And this is the power spectrum at a scale that is really that's crucial for upcoming gravitational lensing experiments with Euclid, for example. And each point here is a different simulation. And what you can see is there's a very strong correlation between how much gas there is in groups of galaxies and how suppressed the matter power spectrum is. To fulfill their potential, these upcoming experiments need 1% accuracy. So you can see this is very small. This is like 0.01 here. And so that gives us a good measure of the baryon fraction, or conversely, we need to know this baryon fraction to do these cosmic shear experiments properly. Here is just an illustration of how little we really know about the CGM from a theoretical perspective. Here's two simulations that are widely used, Eagle and Illustrious TNG. They both do a good job in reproducing the galaxy population. But what you can see here is that in terms of how much CGM there is, they differ quite a bit. So this is showing the CGM mass fraction in units of the universal baryon fraction as a function of the halo mass. And what you can see is that they're even qualitatively different. And particularly at low mass, there's a large difference. There's a lot more CGM in Illustrious TNG than in Eagle. Observationally, I don't think we know which one is closer to the truth, but it just illustrates how little we know at the moment. The role for galaxy formation, there's some agreement between these two simulations, even though they differ. This is work from John Davies. This is again showing the CGM fraction versus halo mass. On the left, Eagle, on the right, Illustrious TNG. Now I've shown not just the median curves, but also individual galaxies at point, and they're color-coded by the specific star formation rate of the galaxy. So what you can see is that there is a direct correlation between the galaxy properties, how much stars are forming, and the CGM mass. If there's more CGM, if you're higher in this plot at fixed mass, then you have a bluer color, which means you have a higher specific star formation rate. So that could mean that the CGM is feeding the galaxy, or it could mean that a higher star formation rate gives you a higher outflow rate and therefore more CGM. Well, it's the former explanation in these simulations, and that's shown here. So what is shown here is the same plot, but now it's color-coded by the total amount of energy from feedback relative to the binding energy that has gone into the circumgalactic medium. And what you can see is that if you have a higher CGM fraction, then there's been relatively less feedback energy. So that means that the feedback energy that's coming from the star formation is actually ejecting the CGM. So the fact that you have more star formation, if you have more CGM, is a causality that goes from fueling, in the fueling direction. So there they do agree, these two models. I wanted to spend a few minutes talking about small-scale structure, since that has been popular in the last few years, and I'm a bit worried about the discussions sometimes that I hear in these models. And just to show you that I don't want to bash it, I'm telling you here that for a long time actually I've been arguing that we should pay attention to small-scale structure. There's a paper I did, I don't know, I think more than 10 years ago, an observational paper, where we showed that if you select carbon-4 lines, absorption lines, then you find much higher metallicities than if you select on hydrogen lines, which we did before that. And in fact, you can easily find a population with metallicities of order solar, sizes of order 100 parsec or smaller. And there's so many of these objects that they can account for all the metals, basically, that have gone into the circumgalactic medium. But you can also immediately derive theoretically, which is what we did in this paper, that they must be very short-lived little things. So this could be important, but it could also not be so important for what we're interested in. The question is, does this matter for galaxy formation? Does it matter for the interpretation of observations? Recently, there's been some very exciting developments with the high-resolution zoom-ins of the circumgalactic medium, and the emphasis has been on differences. But I just want to take you through a few of these plots, and let's take a closer look at them. Here's Freke van der Voort, who did the first study of this, I think, and here's her plot. This is showing the difference between a normal simulation, this is done with Arapo, and extra refinements on the CGM. The top panel shows the column density, and the bottom panel is the neutral hydrogen column density. The top one is the total column density as a function of radius for one particular halo. But the first thing to take away is that there's essentially no difference in the top panel. And the second thing to take away is that the differences that are there are not monotonic. They're not, and for those of you who have done zooms and vary something, these kind of differences you see in the top panel are actually smaller than the differences you normally get if you change something random. like run on a different CPU. There could be a difference, of course. It's a little bit surprising that to me that the difference is so much bigger for H1 than neutral hydrogen in the unshielded regime. In the regime where shielding becomes important, you have a very quick change. So that's understandable. But no, it's to me, it's not a huge change here. And we can go to another simulation, to Molly Peoples' work for the foggy simulation, which is quite a bit higher resolution still. Here's metals, where you expect more sensitivity. But if you just look at the column densities or the covering fractions, the first thing you conclude from this is that there's very little difference. Here's the one from Hummels. This is looking at H1 in the top and oxygen 6 on the bottom. The CGM resolution increases from left to right. If we now first ignore these median curves and the dotted line is repeated in each panel and just look at the yellow stuff, you can see that the difference is again very small. Right? If you now look at the top panel and you look at the curves, you can see there's quite a big difference going to 2 kpc in the inner parts. And that's because the median jumps from this yellow bit on the bottom to the yellow bit on the top, because there's nothing in between. So this exaggerates the difference a little bit. Again, the difference is not monotonic if you go increasing with resolution. And in oxygen 6, it's even smaller. So I'm not saying maybe we need to go to much higher resolutions to see bigger differences. And there will be difference in the kinematics. Most of these differences will not be observable so easily. There's another misunderstanding here that something I want to emphasize, is that the CGM zooms are not necessarily higher resolution than the cosmological simulations we've been doing, even in the CGM. So if we compare with the 25 megaparsec Eagle volume and the 50 megaparsec TNG volume, these are both bigger volumes, they have similar resolution. Their resolution is about 0.6 kpc for a density of 10 to the minus 2 particles per cubic centimeter. And this is similar to the resolution of CGM zooms. So that means that for Lyman limit systems and stronger absorbers, which have these kind of densities, the resolution is not higher in the zoom simulations than it is in TNG 50 and Eagle 25. However, for lower density absorbers, the low column density absorbers, it's going to be quite a bit higher. So there you really gain. Now I want to show you some
5 minutes.
Yeah?
5 minutes warning.
Okay, yeah, sure. So I want to show you some new results from a paper we posted last week with Peter Mitchell. I think this is quite an exciting angle that we've took here. So what we've did is we measured in the Eagle simulation inflow and outflow rates and recycling rates of all the galaxies. It was a lot of work, and there's several papers that Peter wrote that report on these measurements. But what we did then here is something different. Is what we did is something that we applied a method that we introduced in 2012 with A.L. Nystine. And there, what we did is we created a semi-analytic model out of a hydrodynamical simulation. So a semi-analytic model has a few different categories of matter, and that's this vector at the top left. So we follow the CGM mass, the ISM mass, the stuff that's ejected from halos, and the stellar mass. And then these masses, you have a set here of differential equations that show you what the evolution is. And each of these coefficients in this matrix is some physical process like cooling, galactic wind from a galaxy, recycling, infall, etc. Semi-analytic models normally try to predict those terms from physical principles. What we did instead is we just measured them from the simulation. We measured them as a function of mass and redshift. Now, why did we do this? Well, that allows us then with the semi-analytic model to reproduce the simulation, but also allows us then to change the simulation. What we can do is then to say what happens if we increase the galactic infall rate or if we increase the recycling rate. And this is, so we can, individual specific process we can change and see what that does to the predictions of the simulation. So that is shown here for stellar mass and the stellar mass halo mass relation. I'm not going to go through this, but I want to contrast this with the CGM, which I'll show next. So what is shown here is in each panel is something is varied. The top left panel, we vary the efficiency of halo accretion. The bottom left, we vary the efficiency of accretion from the CGM onto the galaxy. The second column is outflows. The third column is the importance of recycling. Sorry, something switched here on my screen. What do you see now? Because I see two things at the same time.
We see your first slide, but not in full screen mode.
Let me then, I still in full screen out of my own screen, it's a bit strange. Okay, so it doesn't matter, I'll just go back. So now you see it again, right?
Yeah.
Okay. And the top right one is the gas consumption time scale. And we just vary these things up and down, and this is what you get. So you can see for stellar masses, recycling is not so important, for example. Now I'm flipping to CGM. So in this case, we have the CGM mass fraction on the y-axis. If I go back and forth, then you can see that there's a big difference, for example, for recycling. So for recycling, for the CGM, recycling is important. For the CGM, inflows are important and outflows are very important. The only thing that's not really important is the gas consumption timescale in the interstellar medium. So the CGM really is the best laboratory, much better than the galaxy themselves, to see what's going on with gas flows. The final thing I want to show, do I have time? Because I can also stop here.
A couple of minutes, yes.
But here's is a plot of the kind that you've seen before, where people show the budget of halos. This is from a paper from Nastasia Weyers, where we show the mass fraction of the halo as a function of halo mass in different components, where the total is the gray line, and that is similar to these plots I showed you comparing Eagle and T and G before, that you're missing some baryons of low mass. And then if you ignore this purple line, which is the warm hot intergalactic medium, you can see most of the stuff is in the CGM. Then you have some stars, which are particularly important around the Milky Way, and then you have the interstellar medium being less important. If you do this for metals, then stars get relatively more important. Now, this is the plot you normally show. What we have done here in another paper that Peter Mitchell is preparing is to do something different. Here we take as the budget not what is currently in the halo, but what has ever been in the halo. And this is for halos of 10 to the 12 solar mass in the Eagle simulation. So if you look at the right side, this is as a function of time, the mass fraction is a function of time. And if you now look all the way at the right, that tells you where currently the stuff is that has ever been in the halo. And this whole red bit, 60, 70%, that's stuff that is now ejected from the halo, that has been in the halo in the past. The lighter red stuff is the stuff that has at some point been in the interstellar medium. The dark red stuff has never even been in an interstellar medium, it's just been ejected from the CGM without having been in the galaxy. And the stars then, and the CGM you can see next. In the CGM, we also divide this in these two colors, where the lighter blue-green is the stuff that has been through this ISM, and the darker one is the stuff that hasn't been through the ISM. So this gives you a different picture. And here's the same thing comparing on the left baryons, and this right we do it for metals. So if you do this for metals, then essentially all of it has been through the ISM as you would expect. So that's why you miss some of the colors. Okay, I'll stop there.
Thank you, Jo. There is a raised hand, so I'll try this. Graham, you can unmute yourself if you want to ask a question. No. Job, I wanted to ask you if you think that there is space for significant improvement in the simulations and what this would be.
I definitely think there's space for significant improvement because they're very bad at the moment. So there's all kinds of stuff that can be improved. I think despite what I said, I think the extra resolution in CGM is very important and very interesting, so that is for cosmological simulation certainly an improvement. I think if you want to do better beyond that, the main thing is to get a better model for the ISM in simulations large enough to have a good population of galaxies. Currently, simulations like Eagle and T and G and the simulations by Romil and others, and the Horizon simulations, they don't have a cold ISM. So even if we go to 1 parsec resolution, the effective resolution will be 1 kiloparsec, because that's where the ISM start to really differ if you have a cold phase. So that is what we really need to change, and that will change the way galactic winds are generated, for example. That's done by some simulations in zooms of individual objects, like the fire simulations. I think scaling that up is going to be quite important.
Thank you. We have a question from Valentina Ludorico. Should I read it? Yeah, because we are a bit tight on time. Does this last plot mean that all the metals we see in the CGM at redshift 0 were in the ISM of the galaxy before?
Of a galaxy before. This
Of
plot doesn't distinguish whether it's the main progenitor or another one. But yeah, it's not actually all of them, because there's also some stars floating around in intergalactic space, but almost all of them. Yeah. But you can see on the left panel that it's not true for the baryons in the CGM. Most of the CGM doesn't come out of the galaxies, but a significant fraction does.
Okay, thank you. I think we have to move to the next speaker. Thank you, Joop. The next speaker is Freki van der Voort, who is talking about the effect of magnetic fields on the CGM.
Yes, thank you. You can hear me. You can.
Yes.
Can you see?
Yes, we do.
You see this presentation?
Yes.
Okay, then let me start. So it's great to be here, and I will talk mostly about one of the things that Joop just mentioned, the effect of magnetic fields. And let me also say that 2 years ago, if you'd asked me, I would not have expected to be giving you this talk, because I thought magnetic fields were interesting in their own right, sort of as a diagnostic, and I thought that they wouldn't have that much of an effect. And now I believe that I might have been wrong. So let's so as Joop said, there's different ways of simulating galaxies. So I have been using zoom-in simulations that are based on both the galaxy formation model and the initial conditions from the Auriga project, and adding some additional resolution in the circumgalactic medium, because that is what I wanted to study. So we have 1 kiloparsec for all of the low density gas, or better for some of the denser CGM gas. So I've been focusing on Milky Way mass halos, but we have a new extension also to lower mass halos as well. So this movie is from one of the non-refined normal Auriga simulations, and I'm just waiting for this gas metallicity to fade into the magnetic fields, because that's what I'm talking to you about today. So this is like what it looks like for the galaxy. So we'll be mostly focusing on the halos, but it looks very cool. So this is what it now looks like on the sort of the, this is a 800 by 800 kiloparsec image that goes well beyond the virial radius. And this the simulated galaxy has been moved edge on. So we're seeing an edge on projection of the magnetic fields on the left and the metallicity on the right. And you can see these faint lines, these contours, they indicate the magnetic field direction and the velocity direction. So I just mostly wanted to show you what it looks like, and also say that there's a correlation between high magnetic field strengths here in the sort of polar directions of the galaxy and high metallicity, because both of these were primarily pushed out of the galaxy by feedback. So then, so I started. So these simulations are sort of the normal way to run them is with MHD, because why would you not? You have magnetic fields if you can. So I sort of had to take a step back and run the extra ones without magnetic fields. And then the way that I've done this is by just setting the seed field that is initialized at the start of the simulation at redshift 127 to 0, because if you don't have any seeds, then you will not ever generate any magnetic fields. So it's the exact same solver, the exact same galaxy formation model, the exact same resolution everywhere. The only thing that's different is the seed field at redshift 127. So this results in either no magnetic fields or the magnetic fields that are generated within for this galaxy, for these initial conditions with our galaxy formation model. So the one I'm showing you today here is the one I'm focusing on. And here I've taken everything that is the normal Auriga model, except I've switched off AGN feedback, but the results are qualitatively the same, even if I had used AGN feedback. And I've also run it with the TNG galaxy formation model. And again, qualitatively, it'll be exactly the same. It's just I'm showing you this one because the differences between with and without magnetic fields were largest for this this pair of simulations. So in the top panels, you can see the density, temperature, and pressure without magnetic fields, and bottom panels, the same ones with magnetic fields. And these are slices, not projections. So it's easier to see what happens sort of at the, at the very small, the smallest scales that we can probe with these simulations. So what I want to show you is just how different the structure is. This is sort of hard to quantify when you're making, averages, like radial averages or something. So you won't really see exactly what the structure looks like. So just wanted to point out that there's a lot of sort of random, turbulent, fine scale structure without magnetic fields, and you get much more of these filaments when you have magnetic fields. And this, the addition of magnetic fields also ends up in smoothing the pressure of the CGM. So you get a lot more fluctuations when you have only thermal pressure. So this is a total pressure, thermal plus magnetic. Okay, so this is then a slice through the simulation to show you what the magnetic field strength is. So you can see it's fairly high in the outflow direction and relatively low in the disk plane, away from these conical outflows. And so again, this is exaggerating sort of the importance of these outflows, because if you would make a projection, you would also project a lot of the line of sight that isn't exactly in the outflow. So it's just enhancing this difference. So even though this is a 2D image and you think like, oh, is that quite important? Overall, if you think of the halo as a 3D thing, then the total volume is actually quite low magnetic field strength. And if you divide the two pressures, then you see that for most of the volume, the thermal pressure dominates by 2 orders of magnitude. So this is also true here in the disk plane, so that just the magnetic fields appear to be completely subdominant. But just to go back to this plot that I just showed you, even though the magnetic fields are not dominant in this regime, you still see a lot of differences in the structure, but also in the actual temperature and the pressure as well. So important, I think, to keep in mind that they can still be important even when they don't dominate. So now here I'm showing you the sort of the more quantitative differences so it's the outflow velocity in the top panels, just all the gas that has a positive velocity, and then the inflow in the bottom half here. So this is just all the gas with a velocity less than 0 as a function of radius. So the galaxy will be here in the central 25 kpc or something, and the virial radius is just outside 200 kpc, depending on exactly what your virial radius definition is. So without magnetic fields, we're getting outflows and inflows of approximately 50 kilometers per second, depending slightly on radius as well. But for our simulations where we don't have magnetic fields, both the inflow and the outflow are much higher velocity. So they are enhanced by, so the outflows are enhanced by, a factor of 3 or so, and inflow speeds are also on average about a factor of 2 higher. So this is quite a difference in how fast the gas is moving into or out of the galaxy and the halo. This also has consequences. Sorry? 5 minutes. Yes, consequences for other properties. So we have, so here I can't show you everything today. So the metallicity as a function of radius. So with magnetic fields, we get a very strong decrease. So as you go so this is the average, the azimuthally averaged metallicity. As you go out, the metallicity tends to be a lot lower, and this is because more of the halo is not very much enriched. It's still enriched in the outflow direction, but not at all in the areas sort of in the disk plane, whereas it's much more flat with magnetic fields, and that is because the metals are much more mixed. We also get very different amounts of baryons and metals contained within the virial radius or within any radius. So this is a cumulative plot. So it shows you the total gas mass within a radius, and you can see that it's up to a factor of 2 different here in the inner CGM, but there's still a substantial difference also outside at the virial radius. And this, as you go, I mean, the total amount of metals is approximately the same. So as you go farther and farther out, this difference disappears, and this is approximately at a megaparsec away from the galaxy. So here's this, what I was talking about when I showed you this metallicity as a function of radius. It's sort of hard to take azimuthal averages because it is so different in the outflow direction versus the rest of the CGM. So without magnetic fields, we can see here on the left, and with magnetic fields on the right. So what you can see is that the metallicity is the highest in the outflow direction, but you enrich a lot more of the CGM to relatively high metallicity when you don't have magnetic fields. So these outflows that are metal enriched are much more collimated and mix much less with the rest of the CGM when magnetic fields are included. This is one way to quantify this, is by now plotting it rather than as a function of radius, as a function of azimuthal angle. So we have the disk plane here on the left, and well, the polar axis on the right. So there's a strong dependence, and Celine will talk about this later. But what I wanted to mention is that the scatter is very different at fixed azimuthal angle. So you get a much larger scatter in the velocity without magnetic fields, and a smaller scatter when magnetic fields are included. And the opposite is true for the metallicity. So you get a much larger scatter when magnetic fields are included. So this again shows what I've been saying, that these outflows are actually more collimated and less well mixed. So they end up having more similar velocities, but more different metallicities because of this decrease in mixing. Why this is hard to say. So it could be actually set very close to the disk at sort of the launch of these outflows, or it could be sort of the in situ large distance turbulence out in the CGM that's different. This is a little hard to probe with our simulations, but definitely something that I'm keen to investigate in the future. This also relates to differences in the galaxy itself. So you end up changing the angular momentum of the accreting gas, and you end up with larger galaxies when you have magnetic fields included. And this is a simulation that finished running yesterday, and it's only a 10 to the 11 solar mass halo, so it's only one galaxy, so maybe you shouldn't trust it yet. But I wanted to show you that, so here we have this outflow-inflow plot again, with and without magnetic fields, seems pretty similar. And then the metallicity again looks quite different. And here this is shown visually. So it seems like it's less important for these lower masses, and but still non-negligible for at least some of their properties. To answer this question, so there's a lot of things I could say about this, but let me just say that I think, so I believe now that the structure and properties of the CGM depend on magnetic fields, and these can and will be constrained observationally. So here's a plot from Pakmore et al., and here's some upper limits that are very recent. So they're not yet starting to, they're not yet very constraining, but these are just the first ones. So hopefully they will become, there'll become more and more constraints as more fast radio bursts are discovered that probe the CGM. And then I wanted to just say that all, like, these properties also depend on exactly what your feedback model depends, at least for some things, on the resolution of the simulation. There's potentially other missing ingredients, so that Joop already talked about that. So I'll just go to my conclusions, which is that the magnetic fields alter the CGN properties. They slow down inflows and outflows. You end up with higher baryon fractions, higher densities in the inner CGM, higher temperature slightly in the outer CGM, and a smoother pressure, and decrease this level of metal mixing. So I think the observations can definitely be used to test theoretical models, but we also have to take into account that we actually understand what the effects are of other things that may not be included. So that I'll leave it there. Thank you.
Thank you. We have time for only one quick question. KG Lee asked if you try to split the inflow-outflow into ionized versus neutral gas.
What is the specific question?
So did you try splitting the inflow-outflow, I guess, with and without magnetic fields into ionized and neutral gas?
So I have looked at some things for just the H1, so you still get a dependence on the azimuthal angle, and you still get a difference in the scatter. I haven't remade all my plots for just the neutral gas, so I guess I don't know. Like I don't know all of the things, but I would imagine that it would hold there as well. I mean, none of the gas is 100% neutral, right? So even these trace amounts are enough to align the gas flows with the magnetic field direction. Yeah.
Okay. Thank you. We have sadly to move to the next speaker, which is Jake Bennett, and he's going to talk to us about resolving shocks, filaments, and the CGM.
Excellent. Can you hear me all right?
Yes.
Good. Can you see my screen?
Yeah.
Okay, good. So yes, hi, I'm Jake. I'm a PhD student at the IOA in Cambridge. And yes, I'll be talking about some work from a paper published last year, talking about one of the things that Joop referred to, looking at resolution in the CGM and how that affects different things. So, as Joop said, the resolution can be quite important, particularly in the CGM, and that tends to require additional refinement. There are some simulations now like TNG50 that kind of have a uniform, very high resolution, but they are quite expensive generally. So you kind of, you generally require kind of a targeted refinement. A lot of people have been working on this. And as Freke and many other people have shown, the amount of cold gas you get and the morphology of cold gas you get changes with resolution as quite a bit. So if that could be through resolving more processes, physical process a bit better, like turbulence could be one of them, which I'll talk about a little bit later on. Or, for example, resolving like the turbulent mixing layers from described by Max and Peng. So you start to see cold clouds precipitating out of the hot halo and growing. But yeah, that's what I've been kind of investigating, what happens when you boost resolution. So to do that, I've been looking at a very massive 10 to the 12 solar mass halo at redshift 6. So it's a big beast for its time. And I've been using a repo and been using the feedback model from Fable, which is based on the original Illustris, but with a modified AGN feedback scheme. But the difference, what I've attempted to do is kind of similar to some of the other works that Joop referred to, is tried to boost resolution within the CGM by targeting shocks. So as the simulation progresses on the fly, we identify shocks as we go along and boost resolution around them. And we've boosted the mass resolution by a factor of about 512, which is corresponds to a mass resolution of about 3 times 10 to the 4 solar masses. So which is compared to the 10 to the 7 of fable originally. So if we actually apply this scheme to the halo, we get something looking like this. So this is the Voronoi mesh that Arepo uses to discretize the computational domain. And on the left, we have the base refinement run. And on the right, what it looks like when we activate our shock refinement scheme. And what you can see is we start to really pick out the inflowing filaments much better, because they have shocks on either side of them as gas accretes onto them. So we actually boost the resolution in them quite nicely. And so yes, then what physically does this look like? What changes in the halo do we end up with? If we look here, we see that we have temperature maps on the top and metallicity on the bottom. So going from the base to the shock refinement, the clear thing that has changed, there are a lot more cold gas structures in the CGN. By mass, it's about a 50% increase within the accretion shock, which I'll come to talk a little bit more about in a moment. Mostly driven by an increase in the number of filaments penetrating into the hot halo that also penetrate deeper and are denser and deliver more gas. They generally correspond to metal poor primordial filaments, which you can kind of see in the top right of these panels. I'm not sure if you can see my mouse, but at the top right of the right-hand panels, we can see the cold gas corresponding to white metal poor filaments penetrating. So we can already see we're starting to develop a mixture of different phases and a much more multi-phase CGM that's more in line with observations at lower redshift, just by boosting resolution without any other changes. So if I also look at some other properties like cooling rates, for example, because we have denser filaments and a lot more cold clumps, we have boosted cooling rates throughout the halo. Because more gas lies at the peak of the hydrogen cooling curve, effectively. And then specifically looking at the shocks themselves, so this is a slice of a thickness about half the virial radius here. For the base refinement run, we kind of see, you can see the accretion shock in yellow-white. It is quite broad and not particularly well defined in some areas, but if we boost the resolution, we get this quite nice coherent structure where you can see filaments as well, and the shocks on either side of filaments, for example, at the top right of these panels. And we kind of end up with higher energy dissipation at these shocks as well. And because with a better refined as well, as I'll talk about a little bit more, we get more turbulence as well because of the curved accretion shocks. So having a better defined accretion shock allows us to look at that in 3D a bit more clearly, which looks like here. You end up with this potato-like structure that's very much not spherical and does not really, it doesn't directly correspond to the virial radius at all. But this kind of bounds this, what I would call at least the CGM of this massive halo. It's the hot halo, the edges of that. And what you can see, if you color the shock by the local Mach number, you see there are some regions with a very high Mach number where you get a lot of this shock heating of inflowing gas. But there are plenty of regions where actually the Mach number is very low or non-existent. And if you plot on the top of that, the locations of filaments, we can see. Okay, cheers. You can see actually that the filaments penetrate into the halo where the local Mach number is low. So you can kind of start to see how just the orientation of accretion onto a halo, you can already start to develop a much more multi-phase medium. If I look at this a little more quantitatively, we have a significant increase in the hot halo of turbulence and velocity dispersion at the expense of thermal energy and the bulk kinetic energy of this hot phase. So this is a comparison of the change in energy in each phase from the base refinement run is this, at 0, and the dashed and solid are increases in resolution. And if we look at the cold phase within the accretion shock, which I'm showing as this blue band here corresponding to the aspherical potato in the previous slide, we see that the amount of energy associated with cold dense gas is considerably higher within the accretion shock, corresponding to a higher mass flux of about 20%. So you get more gas in the cold phase coming into the halo. So if we look at kind of more optional aspects of this, we find looking at H1, for example, this is partly what Joop mentioned, is that I at least do find an increase in covering fractions, but not so much necessarily within the virial radius, but a bit further out, particularly if you look here, in between filaments, you kind of get these sheets that break up into colder clumps. So you end up boosting the covering fractions and the amount of H1 gas that you have. And this would be quite interesting if we come to lower redshift to start looking at the distribution of that Lyman alpha systems and Lyman limit systems. And having more cold gas implies that you might end up have an impact on star formation as well, which we also looked at. And we have a higher star formation in general, but also it's much more spread out throughout the halo. You have star formation at much larger radii from the central galaxy within the CGM, including in these primordial filaments that are penetrating into the hot halo. This is a fairly simplistic star formation model, that is true, but it's an interesting prediction that we hopefully future observations will be able to tell us a bit more about. And if we look at the actual stellar distribution, so this is a gas density plot in the background overlaid with the distribution of stars colored by the stellar metallicity in that bin. We find that the stars are much more spread out and much further out from the central galaxy. But also, and we can start to see that we really have these metal poor stars forming in these filaments that are then accreted directly onto the halo, which has quite interesting consequences for galactic archaeology and various things like that. In the last minute or two, I have some preliminary results from starting to push towards slightly lower redshift. We're still quite high redshift at redshift 4, but getting slightly more accessible perhaps to observations. And we find that qualitatively, the trends seem to be persisting. We have more cold gas, more filaments penetrating, and the H1 covering fractions increase, again, particularly in and around and between inflowing filaments within the circumgalactic medium. And to answer or attempt to answer the question of the conference, I would say we are sort of fulfilling its promise. The CGM is very important, as Joop described. It's where inflows and outflows and meet, and it's what all the processes that drive galaxy evolution mix in the CGM, but it is quite difficult to simulate accurately. Particularly for large samples of galaxies. We have things like TNG50 that do that, but they are expensive. And so, interestingly, like I and a number of other people have found now that we're not converged on the amount of cold gas that we have, even pushing. So progress has been made, but yeah, there's a lot more work to do from both observation and simulation side. So if I just come to my conclusions, we have developed a new scheme to boost resolution in the CGM and around shocks, which leads to more cold gas, more star formation, and lots of different changes in the property, which would have observational impacts that we believe will persist to lower redshift 2. So thank you very much.
Thank you, Jake. We have a question from Joop, who is saying, beautiful simulations. You said there is a lot more cold gas in the refined CGM simulations. Is this really true? In the papers I showed, that Joop showed in his talk, NH is nearly the same, just NH1 changes a bit, but H1 and H are at the same temperature. In your simulation, do you find a significant difference? But isn't that mostly because your unrefined simulations have very low resolution? Yeah, I I think that's the question.
Yes, so we do find, by mass, we do find a significant increase in the amount of cold gas. Yes, our base resolution simulations are quite low, and some people, like the work from Joshua Suresh, they start off from quite high resolution simulations and then boost resolution further and find much less of a difference. But I guess we were trying to compare to some of the large box simulations like the TNG 100 type things and Fable, and seeing what the differences were. But yes, we find at least more actual mass in the cold dense phase below kind of 10 to the 5, 10 to the 4 Kelvin.
And I also had a very quick question. So I was intrigued by the fact that there is more stellar mass outside of the main galaxy region. Do you think this is something, is the difference is significant enough that we can observe it?
So while observation is certainly not my expertise, I spoke to Roberto Malino about this, and he thought that if kind of the star formation in filaments is above a certain surface density, even at redshift 6, then it's possible that JWST might be able to observe it. So hopefully it would be something we can probe. At lower redshift, I think it will hopefully be more accessible. But yeah, I suppose you have to look at the epochs where this filamentary accretion does dominate. So generally quite high redshift, but hopefully it is something that a prediction that we can test.
Okay, thank you. Just last word. So Joop replied that TNG 100 has better resolution than your base simulation. So maybe suggesting you to try using that. We are also, sorry.
So just very quickly, yes, we do test kind of 2 levels of resolution in my paper, and the cold gas mass does increase again. So yeah, I don't know is the honest question. We find more mass, but it's not necessarily a uniform thing. But thank you for the question.
Yeah, we're also starting to collect the unanswered questions on a Google Doc that we can then share, such that the speakers have the opportunity to interact offline with the people that have asked the questions. We have now to move to, thank you, Jake, again, to Rajeshwari Dutta, and her talk will be about cold metal-enriched gaseous halos around galaxies. So. Hi, Rajeshwari. We don't hear you, although you're not muted. Maybe you want to try without the headphones, or
I guess if Rory is ready, maybe we can just go to the next one and then we'll go back.
While we troubleshoot the problem, we move to Rory McKenzie, who is going to talk about something possibly similar. So mapping the CGM around faint quasars at redshift 3. Hi, Rory.
Okay. Should I just, can you hear me?
Yeah, you should be able to share your screen.
Let's try this. Okay, I hope you can see that.
Yes, I do.
Right.
Okay.
Okay. It's good I came back when I did. So hello, for those of you who don't know me, I'm Rory McKenzie. I'm at ETH Zurich, and I'm going to talk to you today about mapping the CGM around faint quasars at redshift 3. So I was going to say we just heard some nice results on absorption, but that doesn't work anymore. So I will say that emission is highly complementary to absorption, that it gives you a sense of the 2D properties of the CGM. So there's this 1D picture, but it comes with a lot of ambiguity and difficulty in actually interpreting it. So I'm going to talk today, if this slide will change, about quasar Lyman alpha nebulae. So this was one of the first results from Muse, that hyperluminous quasars at redshift 3 had these ubiquitous giant Lyman alpha nebulae of 100 to 300 physical kiloparsecs in size. This very extended emission has been used to constrain the density distribution of the cold gas, the chemical enrichment, even the gas fractions of these massive halos. But a lot of the constraining power of the data is limited by the major uncertainty in the dominant process driving the Lyman alpha emission. It's not clear if the Lyman alpha we're seeing is powered by recombination from the ionizing luminosity of the quasars, or if what we're seeing is Lyman alpha that's been resonantly scattered from the quasar broad line region, or if there's a contribution from collisional excitation. And so to sort of shed light on this problem, what the experiment that we've done is to look at much fainter quasars. And the idea being that, at least in recombination and scattering scenarios, the emission is powered by the illumination of the quasar. And so if we try to connect emission to this very diminished illumination, maybe we can see something interesting. So we've targeted 12 much fainter quasars, basically as faint as you could reasonably go without observing non-quasars. So this is just a plot of our selection function, which is quasars around about redshift 3.2. In terms of the I-band apparent magnitude, and this other quantity, which is basically the brightness of the peak of the quasar's Lyman alpha line, which may be important in the scattering scenario. And here you have the bright sample and our new faint quasar against the parent population from Sloan. So we span a pretty big range in luminosity, but also in terms of Lyman alpha properties of the quasars. For all of our faint sample, we observed them for an hour each with Muse, exactly the same as the bright quasars. So we have a nice consistent data set. So these are optimally extracted Lyman alpha surface brightness maps of our faint quasars. So again, even going 5-6 magnitudes fainter than the bright quasars of this Borisova sample, we still detect nebulae in 100% of cases, although some of them are, borderline, but still there. They have sizes of about 60 to 190 kiloparsecs, so they are generally smaller than the bright quasars, the nebulae around bright quasars. What you probably can't tell from this is that these things are ordered by luminosity, so 1 is the most luminous quasar, and 12 is the faintest. But you see there's not a strong gradient in nebula size or surface brightness. One interesting thing we can look at is the Lyman alpha spectra of the quasars and the nebulae. So in each panel, in gray, you have the Lyman alpha line of the quasar, and in blue, you have the corresponding nebula spectrum. So these are in totally different apertures, but the fluxes haven't been rescaled in any way. So when you look at for the theorists, when you look at the spectrum of a luminous quasar, they have these enormously broad Lyman alpha profiles. What we see quite frequently with the faint quasars is that the quasars have these narrow peaks. These are still broad line quasars. They still have underlying broad Lyman alpha lines. They just have these narrow peaks as well. And what we can see with Muse for the first time is that in a lot of these cases, the nebulae spectrum actually match up with the spectral profile of the narrow peaks. You can see that in a few cases. They have the same spectral profile. So this is interesting, and I'll come back to it. Okay, so I said the nebulae were smaller, but the size isn't really a physical thing. It's just defined by our surface brightness sensitivity limit. So now I've constructed surface brightness profiles of the Lyman alpha emission, just circularly averaged as a function of distance from the quasar. In red, you have the bright quasar sample from Borisova et al. And in blue, all the faint quasars. Sorry?
5 minutes.
Oh, okay. So the black solid line is the median profile for the faint quasars. So you can see that indeed our fainter quasars do host fainter nebulae. But our quasars are about 30 times fainter in UV continuum and only about 5 times fainter in surface brightness. So it's far from a linear dependence. So if we combine the bright and the faint quasar samples, we can maybe study this luminosity dependence object by object. So here, each line is a nebula. Is the surface brightness profile of one of these nebulae, and it's colored by the luminosity of the host quasar. So in this left panel, I'm showing you the I-band absolute magnitude of the quasar, so the UV continuum luminosity. And you see that indeed the red ones, the more luminous ones, generally have brighter surface brightness profiles. But it's not a clear correlation by any means. There's scatter. There are faint quasars which have bright nebulae. On the right, however, I'm using the brightness of the peak of the quasar's Lyman alpha line. And here you see the correlation appears to be much tighter. There's much less scatter. So maybe we're seeing that there's a tighter correlation with the quasar's Lyman alpha than the UV continuum. And you can see that definitely here. On the y-axis is the surface brightness in some aperture of all the nebulae as a function of the I-band absolute magnitude on the left, and again the peak of the quasar Lyman alpha line on the right. And you see what I said, the correlation is stronger with the Lyman alpha than with the UV continuum, much stronger in fact. You can also see that in the faint quasars, the correlation appears to be tighter for the faint quasars than the bright ones, even though the observational uncertainties go the other way. So can we explain these correlations? Well, it's a bit ambiguous. In terms of the correlation between the UV continuum luminosity of the quasars, we think this is probably explicable in either recombination or scattering scenarios. Simulations are needed. It can probably be explained if there is some secondary properties of the quasars which depends on the luminosity. For example, the opening angle of emission or the halo masses. And these factors would then influence the brightness we see in the Lyman alpha nebulae. Yeah, it's ambiguous at the moment, and we need simulations to better understand how the different properties interact. The correlation between the nebulae and the quasar Lyman alpha is a bit more concrete, but still difficult to interpret. Initially, this might seem like the smoking gun saying that these nebulae are powered by scattering, because if the nebulae are powered by scattering, you might expect if the quasar's Lyman alpha luminosity was to double, then you would see the nebula double in brightness, and that's what we see. But actually, this isn't the only thing that's happening. At the same time, the ionizing luminosity of the quasar is greatly diminished in the faint quasars. So we would expect the neutral fraction of the CGM to increase for the fainter quasars. And so we wouldn't expect actually a linear relation. And when we correct for the change in ionizing luminosity, there's no real significant smoking gun for scattering, although we certainly don't rule it out. Perhaps the explanation for this is much more simple, and maybe just the narrow peaks that we saw in the quasar spectra are actually just the inner extent of the nebula that we see going all the way to the center. And then the inner parts and the outer parts are just naturally correlated. Okay, so I realize I'm running out of time, so I'll just put up my conclusions. And you can read them. To come back to the topic of the meeting, we haven't really gotten to the bottom of this issue, and this prevents us from making strong inferences from our data. In the near future, hopefully we can break this degeneracy in the emission process with JWST H-alpha spectroscopy. If this is recombination radiation, then we should see H-alpha. And also in trying to do imaging polarimetry of the Lyman alpha nebulae to see what contribution is there from scattering. And hopefully when we get to the bottom of this, then our data will be much more powerful than they are now. So, right, I'm done.
Thank you, Ruri. We have a question from Valentina Dodorico. She's asking, do you have enough resolution in your Muse observations to understand whether the brightest nebulae in your faint QSO sample are due to the presence of companions?
So the brightest nebulae that we have is pretty, I can show you the picture. It's pretty circularly symmetric. It's not, this is, oops. Sorry. Yeah, I haven't checked in like continuum, but generally we're not super sensitive there. The observations are really only an hour deep, but the brightest object in our sample is this one, number 6, which is, it's pretty round apart from this filamenty thing. So I guess it's not, it's probably not companions. It's certainly not a spectacular example like some of the examples in the bright quasar sample where you had nearby AGN and things like that. We don't really see any evidence for that.
Okay, we have to move back to Rajeshwari, but there was another question for Ruri, so we'll collect it and then you'll have a chance to answer it. So we're back to Rajeshwari from Emma's computer.
Can you hear me now?
Yes.
Okay, good. Let me.
And so her talk is cool metal-enriched gaseous halos around galaxies.
Can you see my presentation all right?
Yes.
Okay, so thanks, Matthew. Hi, everyone. I'm Rajeshwari, a postdoc at Milano Bicocca. And I'll be talking about the recent studies on the cool metal-enriched halos and the connection with galaxies. So to start off with, the question posed by the meeting, whether the CGM is fulfilling its promise. And let me start on an optimistic note by saying yes. I do think that the CGM is turning out to be a very important component that cannot be neglected in study models of galaxy formation and evolution. And in recent years, observations of CGM, like absorption profiles of different ionic species and their covering fraction, are starting to place useful constraints on galaxy simulations. And I think we'll continue to do even more so in the future. And as you mentioned, when it comes to observational aspects of CGM studies, I think you will agree that one of the major updates or improvements has been optical or integral field unit spectrographs, wide field IFUs, which has sort of enabled us to move on from the era of single galaxy absorber associations to a more complete census of the galaxy population and environment. So in today's talk, I'll be focusing on the observation aspect of CGM using IFU studies. And so in the local universe, nearby universe, we can directly image the diffuse gas distribution around galaxies. I show a couple of examples to the left of the H1 21 centimeter and H alpha emission around galaxies from studies which are focused on the effect of environment and interactions on the galaxy distribution. And with IFUs like Muse and KCWI, it is becoming possible to do similar kind of studies at low redshift. So I see and I show an example to the right from a Muse study of a galaxy group connecting the absorption and the emission in a galaxy group. And though at higher redshift and around normal galaxies, absorption lines still remains one of the most reliable tools to sort of map the diffuse gas distribution. And our group is involved in several studies connecting gaseous halos with galaxies using Muse. So one of these surveys is the Muse Ultra Deep Field, the MUDF survey, led by Michele Fumagalli. It's 180-hour on-source large program with Muse. It's one of the deepest IFU surveys. So it's in this field, which has two bright redshift 3 quasars. And apart from the quasars and the nebulae, there are also other interesting structures like galaxy groups at lower redshifts. And it's complemented by HST NIR GRISM survey, as well as high resolution spectra of the background quasars. So I'm not going to talk much about this, but if you're interested, please check out the references here on MUDF. So in this talk, I'll be focusing on the Muse analysis of gas around galaxies, or the MAG survey. It's also a Muse large program led by Michele Fumagalli, and basically consists of about 5-hour observations, complemented by about 10-hour GTO observations of few fields. So in total, there are 28 quasar fields at redshift 3 to 4. One of the examples of a field is shown here. We have detected thousands of galaxies, and using the IFU capability of Muse, we are we can probe the full cosmological volume, complete down to a given flux limit, up to impact parameters of 200 to 350 kiloparsec. The second component of MAG is the presence of high resolution optical spectra of the background quasars. And we have used this to detect hundreds of absorption lines of magnesium 2, carbon 4, and H1 absorbers, as shown here in the histogram. And so the overview of the MAG survey and the connection with the Lyman limit systems at high redshift is presented in Lofthouse et al. 2020. And the gas and galaxy environment around the quasars itself is presented in Fossati et al. 2021. So you can check them out. In this talk, I'll be focusing on the cool halo gas as traced by Mg2 absorption around redshift 1 galaxies. So I'll be presenting the results in this paper that was recently published. So, so we compiled a complete and uniform sample of about 200 galaxies between redshift 0.8 and 1.5, detected mostly via their O2 emission. And this plot shows the star formation rate versus the stellar mass of the sample. And at the same time, we did a blind search for magnesium 2 lines in the quasar spectra. Examples are shown here. And we cross-matched these two samples. And the first result we find is that majority, that is 67% of the magnesium to absorption in MAG, are associated with multiple, that is more than 2 galaxies, as you can see from the histogram to the right. And an example of one of the fields where we detect multiple galaxies is shown here. So this is the O2 narrowband image where you can see like the galaxies associated with the magnesium to absorption towards the central quasar. So we find that the Mg2 equivalent width on average does decline with increasing impact parameter, as has been found by other studies in the literature as well. So this plot shows the Mg2 equivalent width detections from the MAG survey in stars and the upper limits as triangles, and various other literature studies in open symbols. And the color coding is red for single galaxies and blue for galaxies in groups or multiple associations. So we do find a decline on average, but there's a large scatter. And the Mg2 radial profile at redshift 1 is found to be consistent with the literature studies at lower redshifts, that is redshift less than 0.5. But as I said, we find large scatter at higher impact parameters, which we mostly which mostly arises due to the detection of multiple galaxies in the more recent IFU studies. It sort of hints at a more complex distribution of the metals in these denser environments. So we looked for dependence on various other properties of the galaxies as well. And we find a strong dependence on the of the Mg2 equivalent width on the stellar mass, as can be seen here in the plot to the left. The equivalent width shows an increasing trend with the galaxy stellar mass. The covering fraction as well to the right. For higher mass, that is greater than 10⁹ stellar mass galaxies tend to be higher at any given normalized radius than the less massive galaxies. And other than the impact parameter and stellar mass, we also find a strong dependence on the environment. So we find that galaxies in group-like environment tend to show enhanced Mg2 equivalent width as well as covering fraction. So to the left, the covering fraction for groups is shown in blue, and that for isolated galaxies in red. And within twice the virial radius, groups tend to show 3 times higher covering fraction than the isolated galaxies. And the plot to the right shows the equivalent width for the groups in blue as a function of the group-centric radius. And we also plot in gray a simple superposition model estimate, where we assume that the observed absorption is due to multiple halos along the line of sight in the group. And as you can see, while it can explain about half or 50 to 60% of the observation, it does not explain all of them, indicating that there are likely to be other factors at play here, which is which we think could be tidal interaction between the galaxies in groups or ramp pressure stripping, which could be stripping the metals from the halos of individual galaxies in the groups and boosting the observed the cross section and the Mg2 absorption strength. So, and in the last few minutes, I would like to show the results from another survey, the Quasar Sightline and Galaxy Evolution, or the QSAID survey, where we are trying to extend our study of the galaxy environment and the gaseous halos, extending it to a larger sample of galaxies as well as to higher impact parameters, and also extending the redshift range. So QSAID is based on HST large program led by Bilby and Stott. And it basically consists of 8 hours of NIR imaging and resin spectroscopy in quasar fields, so 12 quasar fields at redshift 1 to 2. And as you can see in the figure to the right, we can probe up to higher impact parameters of about 600 to 700 kiloparsec at redshift 1. Plus, the QSAID survey is complemented by the Muse IFE spectroscopy of the inner 1 arc-minute field of view for 8 of the fields. And we have UV and optical high-resolution spectra of the background quasars. So in these spectra, we have detected, conducted a search for lamina alpha, C4, and Mg2 absorbers, which we are now correlating with the galaxy environment. So some preliminary results from the QSAID survey for the Mg2 halo gas is that we find a dependence of the Mg2 gas on the galaxy overdensity. So this plot shows the Mg2 equivalent width as a function of the overdensity, which we estimate by taking physical volumes of cylindrical volume of, in this case, radius up to 200 kiloparsec, and line of sight velocity 1000 kilometer per second along each of the quasar line of sight. And we estimate the overdensity relative to the average or field number density that we estimate from the full QSAID survey itself. And then in each of these volumes, we also search whether there is corresponding absorption in the quasar spectra. And whenever we do detect Mg2 absorption, we plot them here in stars, color-coded by the average impact parameter. And the non-detections are plotted as upper limits here in arrows. And the below plot shows the incident or the detection rate for 2 equivalent width limits. So as you can see, we find a significant trend, a significant increase in the Mg2 equivalent width as well as the incidence as we go to higher overdensities, telling us that the strongest Mg2 absorbers tend to arise from the overdense regions. And the bottom 2 plots show similar plots, but in this case for the stellar mass overdensity to the to the left and the star formation rate over density to the right. And again, in both the cases, you can see we see an increasing trend for the equivalent width of MG2 as well as the incidence with the over density. Though note that we find a stronger dependence on the stellar mass. So I will conclude with that. So I think statistical complete and like deep galaxy surveys, like for example, the MEDF, which I mentioned at the beginning, in quasar fields where we have high quality quasar spectra, are the way forward for these, in case of CGM studies, to keep revealing even more of its, fulfilling even more of its promises. And in both the MAG and QSAID surveys that I presented today, we find a dependence of the cool metal enriched halo gas as traced by MG2 absorption on the galaxy environment as well as the stellar mass. So thank you.
Thank you, Rajeshwari. If anybody has a question, just feel free to type it in the chat or in the Q&A. There is one question from Valentina Dodorico, which is, how do you define the association between MG2 absorbers and galaxies? Do you use a difference in velocity?
Yes, so we, for the MAC survey, we use the full, we search for associations in the full Muse field of view, which is around 250 kiloparsec impact parameters at redshift 1, and a velocity separation of about 500, plus minus 500 kilometers per second.
Okay, thank you. Thank you, Rajeshwari. So we have to move to the next talk. Kiji Lee is going to talk about fast radio bursts as a probe of the IgM and CGM baryon distribution. We don't see you yet. Maybe there is a technical issue. We now have two shorter talks, and I kindly asked the speakers to try to stay within the time limit if possible. So the first one is Dylan Nelson, and he's going to talk about the sculpting of galaxies and their CGM by supermassive black hole outflows. I'll probably give you a 2-minute warning because 5 minutes doesn't really make sense.
Thanks, Matteo. Can you hear me okay and see the slide?
Yes.
Cool. So hi, everyone. Yeah, very great to join this discussion. Let me jump straight in. So I'm going to talk about how the action of supermassive black hole feedback imprints observable signatures, not only on the gaseous halo, but also on the nearby galaxy population. Okay, so my starting point is that in the illustrious TNG simulations, black holes produce very strong outflows. I'm showing you an example of that here. This is one black hole driven outflow, which is a cocoon-like morphology, a bipolar flow of metal-enriched hot gas, which has been driven to high velocity, thousands of kilometers a second, and to quite large distances, hundreds of kiloparsecs, away from a galaxy at the center, which is a disk-like galaxy here, oriented edge-on, which hosts a supermassive black hole at its center, which, by driving these outflows, is initiating the process of quenching this galaxy, right? As galaxies quench, they're transitioning from the left to the right here, from the blue star-forming population to the red quiescent population. And if we look at the CGM of these two distinct populations of galaxies at the same mass, what we see is that blue star-forming galaxies, for instance, host a large amount of high column observable oxygen-6 in their CGM, but quiescent galaxies at exactly the same halo mass do not. They're deficient, and the reason is because as black holes start to quench galaxies and drive outflows, they also directly physically impact the state of the circumgalactic medium. Okay, but this impact of outflows is not just an integral effect on the entire halo. It actually depends on where in the halo you are, right? So imagine a disk galaxy, and you have a major axis oriented here in the horizontal direction, minor axis in the vertical direction. The question we like to know is, how does the mass outflow rate depend on this angle? And this is what we see, again, from the TNG simulations, that outflows are not isotropic. So outflows preferentially collimate and propagate along the minor axes of galaxies. Okay, keep that in mind. That brings me to the main result I want to share with you today, which is actually about satellite galaxies. Now, this is a very cool new finding, I think, from Nacho, Martin Navarro, and Lisa Pilavich. Let me first remind you, satellite galaxies, relative to their counterparts in the field, are quenched. Right? This is the impact of environment. Now, what we have found in SDSS data is that the fraction of quenched galaxies, satellite galaxies, depends on their orientation in the halo with respect to the central galaxy. Okay, so this is the interactive portion, the quiz of the talk. So the question is, in which direction are satellite galaxies more quenched? Option number 1, satellite galaxies are more quenched along the major axis of the galaxy, so the red dots, right? Horizontal direction. Option number 2 is the opposite. Satellite galaxies are more quenched along the minor axis of the central galaxy. Okay, so take a second to think about this in the context of the outflow picture I presented earlier. Normally I'd let people actually vote in the Zoom chat, but we are very short on time. I'll give you the answer. The answer is 1, right? So we find that actually satellite galaxies are relatively more quenched along the major axis of their central. And this is the result from Sloan. So stacking thousands of hosts, tens of thousands of galaxies, what I'm showing you here is the quiescent fraction of satellites as a function of the angle with respect to the central on the x-axis. We find this sinusoidal-like modulation of the quenched fraction. So fewer quenched galaxies along the minor axis and more along the major axis. A very nice way to visualize this is through the isocontour of quiescence. So what I'm showing you here on the right, this is not a circle, right? It's squished. It's compressed in the vertical direction, which means to get to the median quenched fraction of 42%, you need to be much, much closer to the central if you're aligned with the minor axis of the galaxy. Okay, that's SDSS. What is particularly amazing is that we find the same signal in the TNG simulations. That's what I'm showing you here in green. What that lets us do is to try and go figure out the origin, right? So this could, for instance, be a phenomena of large-scale structure. Say satellites preferentially accrete along filaments of certain directions. But this is actually not what we find. We find that this is a host halo phenomena for the following 3 reasons. First, this modulation is not present in the old Lester simulation. I just remind you, the old Lester simulation is the same volume, the same objects, but with a very different black hole feedback model. Point number 2, this modulation is stronger around quiescent versus star-forming galaxies, and it's stronger for galaxies with more massive black holes. This is true both in data and in the simulations. Finally, this modulation is driven by satellites which quenched inside their redshift 0 hosts, so after infall. Okay, so the physical picture here is then supermassive black hole feedback carves these low density regions in the CGM, in the gas. These occur preferentially along the minor axis direction of the central galaxies. So in those directions, there's lower background density. There's lower ram pressure force, stripping gas from satellites, there's less gas removal along their orbits, and thus there's relatively less efficient quenching of satellite galaxies due to the impact of black hole feedback on the CGM gas, and that's what leads to this angular modulation signal of the quenched fraction of satellites. Okay, so that brings me to my conclusion. The CGM is definitely revealing the process of galaxy evolution. In particular, I showed you how the TNG simulations predict that supermassive black hole feedback imprints observables not only on the gas, but also on the nearby satellite galaxy population. In particular, that this angular modulation of the quenched fraction of satellites lends support to the physical mechanism, actually the ejective nature of the quenching model of these simulations. So I'll stop there. Thank you.
Thank you. I have a question myself. It's a very interesting picture, and it's encouraging that it works both in the observations and in the simulation. I'm wondering though how much the picture itself relies on the fact that you expect like relaxed halos or hot halos for the RAM pressure stripping process, while probably real halos are not relaxed, and so there is a change in density as a function of position in the halo, which could like complicate your signal.
In terms of the shape of the halo, in some sense, that's what you're asking? That the shape is not spherical of a,
yeah, so
gaseous halo.
Like, well, yeah,
I think that's true.
Shape,
we know that
the fact that the
halos...
density locally could change.
Certainly. But in that sense, that's why this point contrasting here, this top bullet point, let me see my mouse, contrasting the illustrious and the TNG simulations is quite relevant. You know, the gas distribution on large scales, the shape imprinted by collapse is the same. But this modulation, this signal is entirely missing when we change the black hole feedback model. So to me, that's a very clear demonstration that the origin is related to the baryonic feedback and not, say, to the gaseous halo shape.
Yeah. Thank you. So people have more questions. Just I think there are a few questions from Joop, but we probably have to copy them in the Google Doc. Thank you, Dylan.
Thanks.
And then we have the last talk of this morning session. It's Knut Trong. Apologies if I didn't pronounce your name correctly. And the talk is going to be on X-ray signatures of supermassive black hole feedback in illustrious TNG and X-ray observations.
Okay, thank you. Can you hear me?
Yes.
Can you see my slide and my cursor?
Yeah.
Okay, thank you. So thanks organizers for providing me opportunity to present our recent works. And my name is Knut Trong. I'm currently a postdoc at the Max Planck Institute for Astronomy. And today I'm going to talk about how study of CGN may review important role played by supermassive black hole feedback in the context of illustrative TNG simulation and current X-ray observations. So indeed, I have only two main messages we'd like to discuss with you today. So the first one is about CGN as purple star formation quenchings in massive central galaxies. As we have heard earlier this morning from Job or from Dylan, in illustrative TNG or in EGO as well, massive galaxies are quenched due to the ejected effect of supermassive black hole feedback, in which the feedback, expels a large amount of gas out of central regions, thereby facilitating the quenching process. And at the meantime, it leaves the quenched galaxy significantly dilated of gas. So the question is, it is suggested by observations. So to address this question, we looked at the X-ray emissions in TNG galaxy across the mass range. And what we found is that there seems to be a kind of diversity in the X-ray luminosity between star forming and quenched galaxy in TNG. More specifically, at the overlapping mass range, the star forming galaxy appear to be significantly more X-ray luminous compared to the quenched counterpart. The difference is about 1 or 2 order of magnitude. And when we compare to the current observation of nearby galaxy from Chandra and SML Newton, the X-ray data appear to tentatively support the picture that predicted by TNG. We also found that this kind of RX dichotomies not only exist in the central regions, but it extends to larger galactic distances, about 5 times the half-life radius. And in this regard, future observation with Rosita may be able to put further constraint on the prediction of the RX dichotomy. The second message I would like to discuss is about the Cgn properties as proxy of supermassive black hole mass. So recent X-ray studies have shown that there is a significant correlation between supermassive black holes and the host atmosphere in the early type galaxies. For example, in our own work, we study about 47 early type galaxies that have X-ray data observed by Chandra. And by December, we were able to categorize how supermassive black hole mass correlated with the X-ray properties of the host gas, like the gas temperature, X-ray luminosities. And what we found is that for a sample of brightness cluster galaxies, we found there are significant black hole X-ray scaling relations. And in those BCG, interestingly, the host gas temperatures are viewed to correlate with the black hole mass even better than the stellar counterparts, such as the velocity dispersions. And finally, we found that those correlations extend far beyond the stellar body, out to 5 times the half-life radius. So being inspired by those observational results, we carry out an accompanying theoretical work looking at the scaling relation, but from illustrative TNG simulations. So what we found is that the TNG also predicts there exists a significant black hole X-ray scaling relation in quaint galaxies, and those scaling relations exist on the way from CGN to ICM regimes. And interestingly, those correlations become stronger and more consistent to the similar predictions at larger radii. So this result suggests that the black hole X-ray scaling relation that we found earlier may be a reflection of more fundamental relation, which is the relation between the black hole mass and their host halos. This black hole halo mass relation in the context of TNG can be can be naturally established thanks to the hierarchical assembly of large-scale structure in which black holes and their host halo rose almost simultaneously via mergers at the high mass end. Yeah, so summary, coming back to the key question of this meetings of whether the study of CGN fulfilling its promise of revealing processes that drive galaxy evolution, my tentatively answer is yes, based on many interesting work that we have heard this morning. And in addition, in our work, we show that CGMs appear to be an ideal place to probe the quenching mechanism of star formation in massive galaxies. And second, by studying the CM properties, we may be able to reveal fundamental correlation between the supermassive black hole and their host halos. Thank you. I'm done.
Thank you. Are there questions? I don't see them. So since your talk was about comparing simulations and observations, on this specific topic of the X-ray emission, do you think we should improve more on the observation side or the simulation side?
So I would advocate for more collaboration between the simulation and simulator and observers, because from my own experience, all of the works that I have shown you here is a result of the collaboration between the simulator and X-ray observer. So yeah, we should have more talk between simulator and observers.
Okay, thank you. So this concludes this morning session. And if I'm not mistaken, Emma can correct me in case, we are reconvening in 55 minutes to start the second session, the afternoon session, and conclude with hopefully very engaging discussion on what we have learned today. Emma, do you want to add anything?
No, that was everything. To say thank you to all the morning speakers. They were all very interesting talks. And we'll see you back here at 1:30 UK time.
So, Emma, do we have any announcement before we start the talks? Or...
No, I think we're good.
Okay, so we'll just wait one more minute and then just kick it off. I'll use 30 seconds to just introduce myself so we can then have an on-time start with Valentina's talk. Hi, everyone. Well, thank you for joining back for this second session. My name is Michele Fumagalli, and I'll be chairing the session this afternoon. I'll remind you that if there are any unanswered questions, you can actually find them in a Google document that Emma has prepared for us. I'll just drop that again in the chat so people can go and find it there. And so if you are a speaker of the session, please check it to just see if there are any questions addressed to you. And I would also ask the speakers of today's session to please keep to time, so we can have a little bit of time for discussion at the end. And we have a very strict time limit of 3:30 UK time, so we cannot go over that. So let's make sure we stay on time. Okay, well, it's 1:30 on my clock, so welcome back. We start with an invited talk by Valentina Dodorico, who's going to tell us about metal set traces of the CGM at high redshift. Thank you.
Okay, thank you. So we'll start sharing my screen. Can you see the presentation?
Yes.
Okay, fine. Okay, so good morning to everybody. And okay, so today we are here to discuss, to try to answer, in fact, this question. And I will give you my answer in 3 points. So, of course, the presentation will be slightly biased on my expertise. And it will be also a bit superficial in the sense that I will touch several topics without going into the details since I don't have much time. In particular, I will not talk of the CGM in emission, although we have heard already a few nice talks about that. So I will focus mainly on the redshift range between 2 and 3, 2 and 4, let's say, which is in fact a privileged epoch to understand, let's say, the evolution of galaxies, because it's the peak of star formation. And it's also a favorable range in redshift observationally, because we have that the strong UV lines are redshifted to the optical. So the first point is what is the CGM? In fact, we have that the concept of CGM is quite recent, if you want. Emma has shown this increase, a very strong increase, in fact, in the number of papers per year mentioning the CGM. But this is also due to the fact that before, let's say that about 25 years ago, when I started working in the field, we were just talking about galaxies and the intergalactic medium. While let's say that I can more or less take as birth of the concept of CGM at the beginning of this century, at least observationally, when appeared a couple of papers. And the first 2 were from Adelberger and collaborators. What they did was to try to find what was the connection, let's say, between the carbon-4 absorbers observed in high-resolution quasar spectra and the Lyman-Breck galaxies in the field. So what they did was to compute really the cross correlation between these two populations of objects. And they found that the correlation length of this cross correlation was, in particular for carbon-4 systems above a column density of 13, was the same correlation length of the autocorrelation function of Lyman-Breck galaxies. So from this information, they derived the fact that there was a very strong connection between these two populations. And furthermore, they, from the impact parameter, let's say, of the galaxies they had considered on the, along the line of sight, they derived that around these Lyman-Breck galaxies, there were bubbles of enriched material extending to hundreds of kiloparsecs. So, well, I mean, distances much larger than the virial radius. Another very important paper for the definition of the CGM was this paper by Steidel in 2010, where instead he used galaxy pairs. So he used a galaxy as a background source and the galaxy in the foreground. And because galaxies are much more numerous than quasar in the field, it was possible to probe on a finer, let's say, grid, the separation, the impact parameter, let's say, characterizing this CGM. And here you see, for example, the information that he obtained. Here he had to consider stacked spectra in different bins of impact parameter, because the single spectrum has a low signal-to-noise ratio. And you see, for example, this line that is the carbon-4, how it decreases as the impact parameter increases. And here you see more quantitatively the variation of the equivalent width of different lines, ionic lines, like for example, the Lyman alpha line or the carbon-4, as the impact parameter from the galaxy increases. Again, from this result, they could derive that around these galaxies there was this let's say medium that was metal enriched and that was extending out to hundreds of kiloparsec. After these initial papers, let's say, there have been a lot of work on, of course, observationally on this subject. And here I tried to list the main, let's say, results obtained at high redshift. In particular, there is a whole series of papers that are dealing with the CGM of quasar hosts, so the Quasar Probing Quasar project by Prochaska and Nawi, and all the papers from the Keck Baryonic Structure Survey that was a kind of development, let's say, of the first work by Adelberger and by Steidel. And I did it here just for reference. So once you accept that the carbon-4 absorbers are good tracer of this CGM, of course you can also use the statistical properties of these absorbers as I mean, to investigate the properties of the CGM. And for carbon-4, as we have also for other, in fact, ionic, metal ionic absorptions, we have really a lot of observables. We have, for example, distribution function of the column density or the equivalent width. We have the evolution, for example, of the cosmic mass density. And we have also a two-point correlation function, for example, that you can compute for in different column density ranges. Along here, you have a result which is obtained along the line of sight or transverse to the line of sight, so considering quasar pairs. And in particular, the two-point correlation function gives you a constraint on the size of these enriched bubbles. Of course, you always need to compare in order to derive then really the physical parameters, the physical characteristic of the CGM, to compare this observational result with simulations. And more recently, but we've seen also from the talk of Joop, and also there is a lot of work also from Michael Ralph and so on and so forth, there are results on the complexity of the CGM, so the real structure of the CGM, the fact that it is a multi-phase, and this information are obtained from multiple line of sight. In particular, for example, here I show you a recent result from the Keck baryonic structure survey, where they use a pair of lensed quasar, which are, so the two images are very close in the angular space, that are probing 400 parsec at the considered redshift. And what you can learn from the figure that is here on your left is that the structure, in fact, of the metal absorption is very quite significantly also on these very small scales, telling us so that the structure, I mean, the CGM is very structured, and the metals are probably very small clumps, embedded probably in a more ionized gas that is traced by the oxygen 6, which is the one that shows the less difference between the two line of sight. Even more intriguingly is the real dissection of the CGM that was possible with this analysis carried out by Sebastian Lopez and collaborators, observing with Muse these two giant gravitational arcs that you see here, that are very close to this galaxy that is here in the inset that is close by the arches, and this gives them the possibility really to probe the CGM at different impact parameters ranging between 0 and 60 kiloparsec. However, these kind of studies at the moment are possible only at relatively low redshift and also at relatively low resolution. So what is the first message that I want to give you here? That there is really a lot of information that is still in the available observation. And I think that in this case, maybe simulators should try to reproduce this, I mean, to use this information. And as also the previous speaker was saying, maybe we should interact more between simulators and observers to understand, for example, what are the observables that give better constraints, for example, on the figure mechanisms, or what are the observables that are more easily obtained from simulation. So I think that still there is some work to do in this sense. So my second point is this one. So are we really able to test inflows and outflows from observation? Well, let's see. And first of all, let's do a step back. And I'm showing again this nice drawing by Jessica Berg that also Emma showed at the beginning, because more or less at the same time of the paper of Adelberger and Steidele, there were also a few groups that were proposing this, let's say, this new scenario, in which the accretion onto galaxies was happening both in two ways. There was the standard, let's say, hot mode, where the particle is shock heated and then it cools and it goes toward the center of the galaxy. But there were also some particles that in fact were going directly inside the galaxy without, I mean, keeping their relatively low temperature. This is the so-called cold inflows. And in fact, this cold mode accretion, at least from simulation, looks dominant at the higher redshift and for the lower masses. So the scenario should be more or less this one. So on the plane of the disk, we have this cold gas that is accreting, while in the minor axis, the direction, we have mainly, let's say, of course, the outflows with some part of the gas that is then falling again onto the galaxy, so this recycling gas, and part of the gas that is instead outflowing and going to the CGM and then also to the intergalactic medium. So first of all, evidence of outflows. Well, let's say that the existence itself of the CGM is an evidence of the fact that metals are able to escape from the galaxy. However, it's true that maybe with the present observation, it's really a bit hard to really characterize the CGM. So where really is this gas going? How far is it going from the galaxy? And all these questions. And then I also would like to report this sentence from the paper of Porciani and Madau that were discussing Heidelberg results, where they say that in fact Lyman-Breck galaxies are living in overdensities, and most likely, in fact, this gas has been pre-enriched by previous generation of galaxies. So the problem is also that at redshift 2-3, let's say what we see in the CGM is really a cumulative effect of all of everything that has happened also before. So of course, also the interpretation becomes more complex. And but instead, do we have evidence of cold inflows? Well, unfortunately, let's say that from absorption studies, at least at the moment, it is not possible to understand whether the gas, in which direction the gas is going. Is it inflowing? Is it outflowing? It's really very complicated to understand this from observation. However, let's say that at lower redshift, where it is much easier to at least to characterize the galaxy, so to understand, for example, its orientation or how or its kinematics. We have several results. There is Céline Peru and her group. There is all this megaflow survey. For example, this result from the megaflow survey is showing that the gas along the minor axis is in general more dusty and more metal rich than with respect to the gas that is observed along the major axis. And also in this case, for example, this extending, let's say, the rotational disk of the galaxy to the position where the quasar is, we have that the velocity that the gas should have is in good agreement with the velocity that we observe for the absorption here, the magnesium 2 absorption. So these are, let's say, observations that goes that are at least in good agreement with the prediction. But let's say that if this was a crime investigation, probably we would qualify this evidence as circumstantial. So should we be really, I mean, should we give up? Should we abandon the field? So my third point is that we really don't have to give up because the future is really very bright, in my opinion. And again, I will make 3 points here. First of all, I think that now we have the possibility to go at very high redshift. And going for what I said before, when we go to higher redshift, also the situation in some sense should be simpler, because the CGM, we should see much clearly the signature of feedback as it is happening. So there has been less cumulative effect, let's say, of the metals going into the CGM. And in this respect, I would like to advertise this survey, the XQR30, that is based on a large program, the X-Shooter spectrograph, obtaining 30 quasars at a redshift between 5.8 and 6.6 with a very high signal-to-noise ratio. And the observations are almost finished. So really with this sample, we will, and using also what is already available, of course, at the same quality, we will be able to build statistical samples of metal absorption and of course also determine their statistical properties. So there will be, I hope, very soon a paper appearing by Rebecca Davis and et al. And furthermore, this sample is also, I mean, will be and is also already being studied with the Muse and ALMA with parallel programs that are in progress. The second point is that we in the near future, really, we will be able to view the CGM in 3D. So already this Muse ultra deep field that is led by Michele has been described. So this is really a precursor of this kind of studies where you can put together absorption and emission information on the CGM. But the future, in particular with ELTs, we will really be able to do this famous tomographic analysis of the intergalactic medium, of the density field. And really, even just going down of half a magnitude will increase incredibly the number of galaxies that we will be able to use to do this kind of analysis. And the third and final point, which is also extremely important, is that we will be able finally to detect directly these inflows. This is really possible now just with a few for a few objects, and this is done by observing directly, let's say, do the direct spectroscopy of a galaxy, so the so-called down the barrel observation of a galaxy. Because here, if you observe absorption lines that are redshifted with respect to the rest frame, they are an equivocal evidence of inflowing gas. And as I said, there are really just a few examples at low redshift, one example at high redshift, but now they are observed at low resolution, so lines are not, so there are a lot of problems at the moment. And this is also a fantastic science case for ELTs. So I will leave you just with my conclusion, and then we'll take questions.
Thank you very much. I have a minute to take one or two questions, if there are any. You can raise your hand if you want to speak, or you can type them in the QA window or in the chat. I don't see many comments, so I'll start asking one. So you were going back on this point of interaction between theorists and observers. And I was wondering if you have, say, one or two specific requests from the observational point of view, or things you'd like to see out of simulations. So it's like, well, especially these new simulations that are introducing new physics.
Yes, of course. I was very excited by those simulations that really simulated higher resolution the CGN. This was a fantastic, of course, experiment. But I've not seen any, let's say, further development of this. In particular, I would really like to see what happens to the metals. I understand that, of course, if you want to follow the metals, maybe you have also to introduce some, I don't know, other processes maybe that are more complicated. But I think that really some observations that are still there and that have not been I mean, no one has tried to really reproduce them and to see what happens, for example, with this new simulation. But in general, I mean, I would say that the simulation where the metals have been treated are less than the general simulation where you treat or where you try to compare observation and simulation prediction for the H1, for example. I understand that it is more complicated, but I think that it gives you also many more information on feedback, for example. So this, in my opinion, is really a bit missing, I would say.
Thank you very much. I see there is a question also for Avery. We'll try to make it quick while maybe Max is setting up and starting to share the screen.
Okay, so I will stop sharing.
Avery, you should, yeah.
Yeah, can you hear me? Yeah. Yep. So thank you, Valentina. That was great. Right. I wonder if you could talk a little bit more about the tomography. I presume that the radial direction is actually in velocity space by looking at high resolution spectra. What resolution, is that true? Or what resolution could you achieve? The reason I'm asking is because I think one of the distinguishing features between different simulations, models, may actually have to do with the velocity spread, particularly as you go, or for example, as you go to high resolution, you start to see fragmentation that's different. But the covering fractions and column densities tend to stay roughly the same, although we had some discussion about that. But in velocity space, there might be real differences, and it might be velocity space that's able to distinguish between different models.
Yeah, so sorry, I missed what was the question? The resolution of the observation that we will be able to obtain. You mean?
Yes, and just actually how that relates to the 3D tomography. I'm wondering if you actually mean that the radial direction will be based on velocity, or do you have another means of getting the third dimension?
No, the third dimension is along the line of sight, of course, because so you are in redshift space. Was it that the question?
Right. Yeah. So what resolution can you achieve?
Well, this we will see which instrument will be available to do this. For example, if I think of the mosaic, let's say the MOS for the ELT, the ISO ELT, the resolution, I think that now they are thinking of a resolution which is about 20,000 or so. So the resolution will not the highest resolution, but it will be okay to, for example, for the H1 absorption, for sure it will be fine. Maybe it will be a bit low for metals, but I think that around 20,000 would be okay for to reconstruct the density field traced by neutral hydrogen, by
Okay, well, sorry, I need to unfortunately cut this because we're running late, but we can continue the discussion in the Google form, so we can have follow-up questions there. And thank you very much for a nice talk. So next up is Max Bonke, who's gonna talk us about big and small multi-phase gas dynamics in a turbulent medium. Take it away, thank you.
Yeah, thanks a lot, Michele. Do you hear me? Is the sound okay?
Yeah, that's fine.
All right, great. Thank you so much. Well, thanks also for for letting me speak here. I have to say that I really like these dedicated small meetings where we don't really have to spend a lot of time on the introduction. So I really want to do that. I just want to highlight the point that was made by the previous speaker, that from observations we know that the cold medium is has a large areal covering fraction, but a low volume filling fraction. So it's thought to be in these small clumps, and I'm going to talk about these small clumps because one of the motivations in a way is this challenge for simulations, and this is a simulation now a few years old by Claude André, and he raised the resolution here from low resolution to high resolution, and that's the neutral hydrogen column density. And we know now from these enhanced resolution simulations that were also mentioned by Valentina, that there's really no convergence there. And questions is when can we reach convergence? What scales do we have to resolve in order to be able to compare these two simulations? And now a few years back, Mike McCord had this phenomenal idea. He thought about what happens if a large gas cloud is cooling, and he said, if this gas cloud is much larger, or the cooling time of this gas cloud is much smaller than the sound crossing time of the gas cloud, then the usual way is to think that it cools on a short time scale and then it slowly contracts on a time scale of the sound crossing time scale. But here you would be wildly out of pressure balance, and nature doesn't like to be out of pressure balance. So instead he said it's taking this path where akin to the gene instability, the cloud shatters, he called it. So it fragments into these small pieces of size CST cool. And here's like two simulations where one time, the initial gas cloud is of order of CST cool. Here it's much larger than CST cool, and you really see in 3D, it fragments into these small pieces. And that was thought, to give you a natural explanation to this fact that we see these very small cold gas clumps around. Another length scale that we discussed was coming from a different idea, and that was, if you think about, cold gas impinged but on by a hot wind, then there is a certain destruction timescale associated with these hydrodynamic instabilities, and this is smaller than the time it would take for the wind, say, to accelerate this cold gas cloud. And we wrote these papers saying, like, okay, if this cooling time of the mixed gas, and mixed here is taking the geometric mean from the hot and the cold medium, is shorter than this destruction timescale, which again is of the Kelvin-Helmholtz timescale of the system, then this cold gas survives. And the interesting thing is that because the left-hand side here is a function of the gas properties, and the right-hand side depends on the geometry of the gas, this also suggests a certain length scale, which is of order of 2 parsec, plugging in certain quantities. So that's really what I want to talk about here. What is it? Is it this shattering picture that we have a fog of tiny droplets, or is it these bigger clumps that only survive if your T-cool mix is smaller than your destruction timescale? And I think that's relevant because, you know, we are in a turbulent CGM, and, you know, it's interesting what is the relevant length scale in this setup. So if we look at a turbulent medium, you know, here I have a hydrodynamical simulation again, where I have a cold gas blob in a hot medium, and I steer the box. Then, you know, you can see that, you know, after a few of these destruction time scales, which again I defined in the same way, but now this time taking as the hot, you know, wind speed before I just take the average velocity, you know, in the box. Then you see that here's the cold gas mass as a function of time. After a few of these destruction time scales, the cold gas is destroyed. And, you know, really similar or you know, akin to this experiments we've done in this laminar wind tunnel, if you vary this ratio of T cool mix to D destruct, so here is unity, here it's 0.1, so this gas cloud is larger by a factor of 10, you know, and I do the same thing, you see that, you know, the upper cold gas is being destroyed, whereas the lower one seems to survive. And, you know, you can map out this parameter space, where here on the y-axis, I plot this critical ratio of T cool mix over T destruct. And on the x-axis is the average Mach number in the box. And the blue points are where the cold gas survives. The red points are where the cold gas dies. And you can see that this criterion coming from the wind tunnel, you know, it approximately works. There's this interesting slope, which, you know, I will come back to later. But overall, you know, it divides this this parameter space into cold gas surviving versus cold gas dying, also in turbulent media. Now, one interesting thing you note is that, you know, on this, you know, close to this survival line, there's some simulations where, you know, cold gas is either dying or surviving very close to each other. And here I highlight these three simulations where, in fact, I start with the same, you know, I run the same simulation just with a different random seed. So I just stir the box slightly differently. And, you know, if I play this, you see, you know, one of them, the cold gas survives, and, you know, two of them, it is dying. And, you know, I'm highlighting this because it explains, you know, in a way why we have this slope. Because if you look at what's going on in these three simulations, and here I plot again the cold gas mass as a function of time, but with the solid line, but also I show, you know, the cold gas mass being in the biggest clump, which is this dotted line. And here in the right panel, I show you, you know, the number of clumps of tiny substructure, you know, also as a function of time. And you know, what you see, maybe you see it even visually if I play this again, you know, what is important to survival is that you have a big clump that is surviving. So for instance, you know, here in this red simulation shown in the red curve, you know, you have a lot of small clumps from the beginning, hundreds of clumps, but you know, your big clump is destroyed very early. And okay, thanks. And then you know, you overall the cold gas cannot survive. So, you know, you need this big clump that's required, you know, that's in a way below this this line to be able to survive in a turbulent medium. Now, what says that about the picture? You know, do we have this fog in the CGM, or do we have these big clumps or relatively big clumps? You know, if you looked at these simulations, you already see in a way the answer, because, you know, what you need is this big cores to survive, as I just told you, but these big cores, they will also shed a lot of tiny droplet around them. So in a way, I would argue, you know, that is this best of both worlds, because these tiny droplets, they give you a very large aerial covering fraction, and a low volume filling fraction, as supported by simulations, by observations, sorry, but these big clumps, they ensure cold gas survival in this turbulent dynamic medium. And, you know, to show this a bit more quantitative, here is, you know, the cumulative mass distribution and the cumulative aerial covering fraction distribution as a function of clump mass now, and just for some simulations where the cold gas survives. And you see that while the mass can be dominated by some of these big clumps, you know, the aerial carrying fraction is dominated by these small droplets. So, that leads to this picture we had, how, the CGM could be made up. And that is, we have some of these big clumps, which we compare to, a few motherships, which are larger than this critical radius. So T equal mix is smaller than this destruction time, and they ensure survival of the whole fleet. But then, they continuously shed this small fighters which have a finite reach, and they're important, of course, observationally, because they dominate the aerial carrying fraction. So you're more likely to pierce through one or many of those fighters. Right, and that brings me to this question that was raised by the organizers, which we should put in a slide or so. I think I have 1 minute left, right? Okay, and so is the study of the CGM fulfilling its promise of revealing the processes that drive galaxy evolution? And I would say for now, yes. And the reason is simply that, the CGM is, in a way, from a theorist point of view, is a relatively peaceful place, to give us a new perspective on galaxies. And, what I mean by that is that in galaxies, in the ISM, we put in a lot of feedback processes, which, we calibrate and so on. And the CGM gives us a new data set, which in a way we can, you check these processes against, in a way blindly, because it was a fairly new data set. And in that way, I think it's a great test site for these processes. And I think, there's been many great papers and studies coming out. So I think, there's, for that regard, it's a clear yes. However, I put this for now there. And the reason is, that I think, in a way, it's an endangered data set, because I think there is, drive towards, using the CGM also to calibrate these models. And I think that evolution is dangerous, because it can lead to that the CGM is just taken as another calibration data set. And in that sense, it would just, increase the amount of data we have, but not really bring us more information. So that's why my answer is that for now, yes. And I'm happy to discuss about this later, of course. Okay, that brings me to my summary in the last 30 seconds or so. I showed you that, cold gas survives in both a laminar or turbulent flow if T equal mix over this destruction timescale, which again is the Kelvin-Helmholtz timescale of this clump, or really Taylor timescale of the clump, which means that, the clouds are larger than R crit of order 2 parsec or so. Then, around this threshold, survival threshold, the stochasticity can lead to, that either cold gas dies or it survives, and it actually grows by quite a vast amount. And, combined, this leaves this cold gas fleet picture of the CGM, where, you have a few big clump motherships surrounded by a lot of fighters, which make up this cloud of droplets with this cores of motherships. Thanks.
Thank you very much. We have time for a question while the next speaker maybe sets up the presentation, please. So if you have any question, you can type it in. The canonical 3 seconds, and then I'll fire away with one on my own. Okay, well, I'll ask one then. So this is very interesting, and as we've seen from Valentina, observers are now developing with this world of observation, where we can most readily map equivalent width as a function of possibly halo mass around galaxies. So is there any chance to translate some of these models in this sort of observable quantities, like equivalent width distribution in halos of different mass? I know this is very idealized, but how can we then bring it back to that world there?
Right. No, of course, I think that that's a good question. And so, the studies I'm, for instance, very excited about, I think Valentina also showed from Gran Rudo and other, which is very high resolution spectra that you can, I think Churchill et al., for instance, is a good example where they basically mapped of how many components do you need, in order to fit such a very complex spectrum. And, if this would be possible, for instance, to do as a function of distance and the function of inclination angle, right, that basically how many, substructures do you have there, I think it would give us some idea about, this fragmentation versus coagulation of such cold gas structures. And I think that would be a good way to go forward.
Excellent. Thank you very much. So I see there are other questions coming in, but we'll put them in the Google Docs. So please go and have a look there. And thank you very much.
Thank you.
We're now moving to our next speaker, Roland Stackax, who's going to tell us about the Muse ALMA Halo survey. Thank you.
Can you hear me all right?
Yeah, that's fine.
Okay, great. Thank you. All right. So I'm Roland Stackax. I'm a PhD student at ESO at the moment. And today, first of all, thank you very much for giving me the opportunity to talk here. And today I would like to talk about the Muse ALMA Halo survey. Let me start right off. So what is the Muse ALMA Halo survey? It is a multi-wavelength study of a large H1 absorber sample. So this means we have absorbers and galaxies associated with absorbers, and we want to see how they are connected. So we study the CGM through absorption lines and the galaxies through emission lines or continuum. So this way we want to trace gas flows, so inflows and outflows, and also link galaxy properties to properties of the CGM. All in all, currently we have 19 observed quasar fields with Muse, HST, US, and HIRIS, with the primary Muse targets are being around redshift 0.4, and they're all strong H1 absorbers. And then we have a subsample of 5 quasar fields where we have ALMA follow-up observations. And all in there, we have 6 absorbers and 9 galaxies. And out of those 9 galaxies, we detect roughly half of them in CO. So I want to go through the results so far a bit. Sorry. So as Valentina showed earlier, there have been, for example, some evidence for a warped accretion disk, which was also traced by this absorption feature found in a quasar spectrum. Also some evidence for galactic winds. All this has been done through, kinematic modeling and seeing how the absorption spectra line up with the kinematic models. Further, there have been some papers about the multi-phase CGM and the molecular gas content in these fields, some about the physical properties. And also what I've been recently working on mostly was studying the different phases within these quasar fields, so the atomic, ionized, and molecular gas. Today, I will mostly focus on this last two due to time reasons. So I would like to start off with the properties of the sample itself. Here you can see on the x-axis the absorber ID, and on the y-axis the number of associated galaxies to that specific absorber. And with associated galaxy, I mean up to 1,000 kilometers per second from the absorber redshift and up to 200 kiloparsec from the quasar sightline. And what we find here is that we usually find more than one galaxy associated with the absorber. So this means, this poses the question, what exactly are we looking at when we study these absorption features? Are we probing the CGM of a single galaxy or the intragroup medium itself? So I think it's really important to study the absorption features component-wise here and try to disentangle these complex systems. Next one, I want to show you the absorption metallicity and against the emission metallicity of the galaxy. And what we find in this sample is that basically all of the detected galaxies have higher metallicities than the metallicity of the absorbing gas, which makes sense in some way. And I think it's nice to see observationally as well here. Another part is the molecular gas content of these quasar fields. So here I'm showing you the molecular mass of the detected galaxies against the star formation rate. I put this together with multiple other Lyman limit systems, sub-DLAs and DLAs. And I'm also plotting two lines, which we'll see in a second, which are the cold gas median and the Phibbs median depletion times, which are basically emission selected samples. And we have here H1 absorption selected samples. And what we can find here with this, I have to admit, a limited kind of data set, is that mostly the molecular gas mass is quite high for the star formation rate. So meaning that, you know, this poses the question: if we look at H1 selected galaxies, do we trace objects that have large molecular gas reservoirs for the star formation rate? As you can see, there's still a lot of limits in this plot. So I think some deeper observations for this would be great to really see if there is something going on here. Then finally, I want to show you what one can do with kinematic models in these systems. So I want to connect the gas and the absorber using kinematic modeling. Here you can see the modeled velocity maps of the based on the CO and O3 line. For this, we used Galactic 3D, so a 3D forward modeling approach. Using cubes to create these modeled velocity maps. And what we do is we extrapolate these modeled velocity maps towards the line of sight of the quasar, which is indicated by this magenta and brown dot on these maps. And now there's quite a busy plot. What you can see here is, first of all, in the first two panels, you can see the absorption features in the quasar, and then the emission lines of the galaxy that is around this specific quasar. And then there's two bars shown, the brown one and the magenta one, which indicate the extrapolated gas velocities of first the ionized and the molecular gas phase. And what we try to do here is using this kinematic modeling and some geometric arguments to see if we can disentangle the system. So first of all, we see that we have a two-component absorption feature, which is pretty much split at the 0 point velocity of the galaxy, or the redshift of the galaxy. And one can see a smaller component which is blue shifted, and a larger component which is red shifted. So what we argue here is based on the rotation velocity and direction of the galaxy. One can see that this smaller component can be part of the extended rotating disk. Although it is rotating slower, it's rotating in the same direction. And also one can see that the extrapolated metallicities of the galaxy up to the point of the absorber is consistent with each other. Then the next point is the larger absorption component that we can see here. We attribute this to infalling gas due to various reasons. First of all, due to geometrical arguments, as Dylan already mentioned before, and Salim will mention in a bit, is that usually the outflows go out in a conical shape out of the galaxy, and we find that the azimuthal angle of this galaxy compared to the sightline is quite small, so around 12 degrees, meaning that it's unlikely that you would find outflows in this geometry. Next, also we check the orientation of the galaxy to see if the inclination is basically negative or positive, and we find that the inclination is a negative sign, and this would mean in this case that that infalling gas would be redshifted. So due to the velocity arguments and geometrical arguments, we see that this is consistent with infalling gas. But this also poses the question, of course, since we see that we have a molecular absorption line there, can we have this molecular phase in infalling gas itself? This was a short overview of a number of things that have been done with the Muse ALMA halos. And here I want to answer the question of this meeting. In my opinion, is yes, at least also in the frame of Muse ALMA halos, we see that this multi-wavelength studies of both the absorption features in quasar spectra and also the emission lines surrounding these of the surrounding galaxies, they can reveal the connection between galaxies and their surrounding CGM. And we can also observe cases, of inflowing and outflowing gas, and also gas that is part of the extended disk of the galaxy. And I also want to mention, I think it's really important to have this component by component analysis of these absorption features, and combine this with kinematical modeling of the emission lines surrounding these absorbers, so we can disentangle all of these complex systems. But of course, the number of observed samples here is still quite low, and as Valentina already mentioned, disentangling what exactly is going on in these systems is extremely difficult, even with current state-of-the-art observations. So this brings me to my conclusions. So we have Muse ALMA halos, which is a multi-wavelength study of a large H1 absorber sample. And I think combining absorption and emission is a powerful tool to probe the multi-phase gas of the CGM regions. Quasar absorbers are not always related to a single galaxy, so we have to think about are we probing the CGM of a single galaxy or intergroup medium. In our sample, the metallicity of absorbers was always lower than the galaxies associated with it. We also posed the question if H1 selected galaxies might trace objects that have large molecular gas reservoirs for the given star formation rates, but more data is needed here. And also, finally, kinematic studies can help unveil the galaxy and CGM connection. So thank you very much. And
thank you very much. We'll take a question while the next speaker maybe sets up the presentation, please. So also there seems to be some delay with which we get the questions in the QA panel. So if you have questions, please submit them throughout the talk so they are ready for us to select. Because unfortunately we seem to get them with a little bit of delay. Okay, I don't see any at the moment, so I'm going to ask one again. So ALMA is a great potential to really give us extremely high resolution, both spatially and in frequency space. So I know that's not trivial, but what are the prospects of following up some of these fields and maybe getting new observation where we can really increase the resolution also in velocity and spatially to basically refine this type of analysis where we try to connect the kinematics from absorption lines to what we see in emission with ALMA.
Mm-hmm. So I think, as you can see in the detection rate, which is roughly half, which is not too bad, but there's the major issue is with low metallicity galaxies. Low metallicity galaxies have basically a really high conversion factor, right? Alpha CO. So I think those are quite tricky to observe, and I think we would have to need to spend more time on those systems if we really want to. Especially concerning, this possible selection bias, I would say, we would have to probe these systems down to 1 gigayear of depletion time, basically set the sensitivity accordingly. That makes sense.
Okay, well, thank you very much. I appreciate it. Thank you for a nice talk. So we'll move on now to our next speaker, Jonathan Stern, telling us about the CGM and rotating disks in fire simulation.
Okay, can you hear me now?
Yeah, all looking good, thank you.
Okay, great, thank you. And thanks to the organizers for organizing such a excellent and short meeting. Yeah, so I changed the title of my talk to pose it as a question. Is a virialized CGM required for the formation of a stable galactic disk? Okay, and what I want to argue in this talk is that the answer to this question, at least according to the fire simulations, is yes. Okay, that we only see stable galactic disks in fire when their CGM is virialized. Okay, that the galactic disks form when their CGM virializes. Okay, and I'll explain each of these terms during my talk. So first, what new observations tell us about when and where star-forming galaxies have large rotating disks? So it's been well known for several decades that in the local blue galaxy population, disks are prevalent only at high masses. When you go to actually to lower masses, the dominant morphological type becomes irregular dwarfs. What more recent imaging surveys have shown us that also when you go to higher redshift, disks become rarer, and actually the morphology becomes much more clumpier and irregular. So these trends with mass and redshift, which we see in the images, we also see them in the gas kinematics. We now have large samples of spatially and spectrally resolved observation of star-forming galaxies out to high redshift. And what these studies typically do is that they model the velocity field inferred from emission lines of high redshift star-forming galaxies into two main components: a rotating component, which is characterized by this V-rot, and a velocity component, which is characterized by this sigma g. Now, because these samples are large, you can actually measure for each bin in stellar mass and redshift what fraction of star-forming galaxies have rotation-dominated kinematics. And as we saw in the images, rotation actually dominates mainly at high mass and low redshift. Okay, when you go either to low masses or to high redshifts, rotation-dominated kinematics becomes more rare, and disordered kinematics are practically the norm. Okay, so this is something that the observations are telling us, that there's strong trends with mass and redshift. And the question I want to address is why. Okay, what physical mechanisms produce these trends? So to address these trends, I'm going to use the fire cosmological simulations. So one thing to note about the fire simulations is that in these simulations, a disk indeed forms. Okay, if you at high redshift, you have kind of these irregular, very messy disks. This is for a Milky Way mass halo, and then the same halo at low redshift has this nice rotating disk. Okay, so these are images from the first file paper. But one of kind of the things that emerged from the fire simulations is that the formation of a disk is associated with additional transitions in the central galaxy. Okay, one transition shown here on the bottom is the drop in the variability of the star formation rate. Okay, you can see here what's plotted here is the instantaneous star formation rate divided by a running mean, and you can see that in this Milky Way mass halos, the star formation rate is very variable in fire at higher redshift. Okay, you see these bursts of star formation, and at some point these bursts just disappear. Okay. And in another transition that we see emerge in fire is the disappearance of galactic outflows. Okay, so stellar-driven outflows. This is shown in this plot on the right from Alexander Muratov's work, where he plots the mass loading rate of outflows as a function of stellar mass. You can see it gradually declines with increasing stellar mass, but above 10 to the 10 solar masses, okay, the mass loading rate just drops. Okay, so the outflows are essentially suppressed. Okay. So we see these kind of three transitions happening in fire emerged. They weren't put in by hand. They emerged in the fire simulations. But what's especially interesting is all these transitions happen roughly at the same time. And to show that, I kind of plotted all these transitions in the same plot. Okay, so this is galaxy kinematics, star formation rate, and the mass flow rate for a single halo, a single simulated halo as a function of redshift. You can see that the kinematics, okay, transition from being disordered, so V0 of the order of sigma at high redshift to a rotation-dominated kinematic, so essentially a rotating disk at low redshift. And roughly at the same time that the disk forms, right, you also see a transition from very bursty star formation to much more steady star formation. Okay, and also these strong bursts of outflows that we see in high redshift, roughly at the same time, they tend to disappear. Okay, so fire tells us that there's kind of three emergent transitions in the central galaxy, which all happen simultaneously. And the question is, which physical mechanism causes these transitions? Okay, and what I'm going to suggest is that these transitions originate due to a qualitative transition in the properties of the circumgalactic medium. Okay, So if we're searching for a qualitative transition in circumgalactic medium, one kind of immediate suspect is this classic division of the CGM into two distinct regimes. Okay, so this is a division which was discussed since the late 1970s. And basically what they say that at low halo masses, when the cooling is when the cooling is rapid, okay, the cooling time short of free fall time, the virial shock is unstable, and the CGM is essentially in free fall. So accretion from the intergalactic medium just crashes supersonically onto the galaxy. In contrast, in high halo masses, cooling is slower, so cooling time is longer than free fall time, and essentially the halo is filled with a quasi-static hot halo. Okay, and accretion is much more gradual. This hot halo kind of slowly contracts and accretes onto the galaxy. Now, this kind of classic, what is done in these kind of classic studies is that they typically take cooling times or free fall times, which are halo averaged quantities. But once you consider the fact that there's a radial dependence of the ratio of the cooling time and free fall time, it suggests that there's another third regime for intermediate halo masses. Okay, you can show that the ratio of the cooling time and free fall time tends to increase with radius in the CGM, and then for at intermediate halo masses, you get an outer CGM which is hot and quasi-static, and the inner CGM is actually in free fall, okay, in supersonic. And we call these kind of CGM, we call them transonic CGM, okay? And the reason we call it transonic is because if you treat the CGM as an accretion problem, then the boundary between the two layers, between the hot and inner layer, is the sonic point of the solution, okay? So the CGM itself is transonic. Now, when we acknowledge the fact that intermediate halos have this kind of hybrid CGM, okay, we should notice that if we're interested in what happens just outside the galaxy, okay, what happens to the gas which is just beyond where the galaxy is, then that gas transitions at this transition, okay, when we go from a transonic CGM to a fully hot CGM, that's when the conditions in the gas just outside the galaxy change. Okay, that matters most for how accretion and feedback work. Okay, and this transition, which is what I'll focus on later, we call it the virialization of the inner CGM. Okay, the inner CGM goes from being kind of free falling and cool to hot and subsonic, and this happens when the cooling time equals the free fall time at roughly 10% of the virial radius. Okay, so this is just a cartoon picture, but just kind of to show you that this is also happens in the fire simulations. I'm showing you here two temperature maps of two different halos, two different fire simulations. These are redshift 0 snapshots. On the left, it's a 10 to the 12 solar mass halo, and you can see that the outer CGM is filled with hot gas. Okay, hot gas roughly at the virial temperature of the halo. If we zoom into the inner part of the CGM, you can see that this hot gas extends down to a few scale heights above the disk. If we go in contrast to a lower mass halo, not much lower, 3 times 10 to the 11, the outer CGM is still filled with the hot gas. Okay, most of the gas here is hot, roughly at the virial temperature of the halo. But the inner CGM looks entirely different. Okay, now the inner CGM is filled with cool gas. Okay, there's a large fraction of the volume which is filled with cool gas. It's much more messier and clumpier, and most importantly, we don't see any clear disk at the center. Okay. So this halo on the right is what we call or the CGM on the right is what we call a transonic CGM, and it indeed materializes in the fire simulations. Okay, so this is showing you two different halos, one which is transonic and one which is hot. But we can also look what happens in a single halo as a function of time. So this is the evolution of the more massive halo with time, going from left to right, from redshift 1 to redshift 0. And you can see that at early times, the cooling time to free fall time measured at 10% of the virial radius is lower than unity, and the inner CGM is indeed non-virialized. Okay, you see all this cool gas, very messy, very kind of multi-phase CGM. And as the cooling time increases relative to free fall time, okay, the gas becomes much more hot until the inner CGM becomes filled with hot gas. So you see a transition both in the temperature, but also in the pressure. So what's shown here in the lower row are pressure fluctuations in the inner CGM. Prior to virialization, the inner CGM is out of sonic contact. That happens because the cooling time is very short. So there's huge pressure fluctuations in the inner CGM. Okay, so that's very important for outflow physics, because if you have an outflow going off from the center of this galaxy, these outflows can easily expand through paths of least resistance. But as time goes on and the CGM virializes, okay, the pressure becomes pretty smooth. Okay, so an outflow going out in the central galaxy here will be essentially confined by the uniform pressure of the CGM. Okay, so we expect this transition in the CGM, this inner CGM virialization, not only to affect how gas accretes onto the galaxy, but also to have a strong effect on feedback, on outflows from the galaxy. This is showing essentially the same thing from a different perspective. Now I'm showing you the gas kinematics, V naught over sigma, as a function of radius and time. At early times, okay, you can see that the gas kinematics are pretty disordered. V naught is comparable to sigma. And as time goes ahead, the cooling time increases. And when the CGM virializes, essentially the central disk becomes rotation dominated. Okay, okay, so what we're showing here is a direct connection between the thermal properties of the CGM and the kinematics of the galaxy.
2 minutes, please.
Okay. And one more thing is the connection to the transitions in the star formation rate and the outflows that I showed you before. So here I'm showing you 3 different simulated halos. They all show the same qualitative behavior. So this is the star formation rate. You see at high redshift, the star formation rate is bursty, and there's a transition. The star formation rate becomes steady. Here the transition happens at the redshift of 0.3. This is another Milky Way mass halo, but the transition happens at the redshift of 0.7. And this is a more massive halo. And again, you see this transition, but it happens at a much higher redshift of something like 3.5. Okay. So, but they all show this transition from a bursty star formation rate to a steady star formation rate. And also in the mass flow, you see transition from bursts of outflows to kind of a steady inflow. And in all cases, this transition corresponds to when the cooling time exceeds the free fall time and the inner CGM virializes. Okay, so it seems that what's driving this transition in the star formation rate and the suppression of the outflows is the virialization of the inner CGM. Okay, so last slide is just a kind of a cartoon picture of what we think is going on, and we're currently exploring this picture with in 3 separate studies led by Zach Hafen and Alex Gurovich and Anna Yu. Basically, we say that this transition, this inner CGM virialization, is associated with the transition both in the physics of accretion and in the physics of feedback. So the the accretion goes from a clumpy supersonic free-fall accretion to a more smooth and gradual subsonic accretion. And Zach will talk about this more in his talk. And the feedback goes from winds being able to expand into low pressure channels to winds being confined by CGM, the uniform CGM pressure. And what we believe is happening is that when you have this kind of violent accretion and feedback, you get a galaxy which repeatedly blows itself up in these cycles of inflows, star formation, and outflows, while only when you have a virialized CGM and kind of more gentle accretion feedback, then you get a stable disk with a steady state star formation. Okay, so that's it. This is my summary. 2 main takeaway messages. One, that there's a third regime for the CGM beyond the classic cold and hot regime, a transonic regime where the other CGM is hot and the inner is cool and free falling. And that the fire simulation suggests that the virialization of the inner CGM, okay, a transition from a transonic CGM to a hot CGM, enables the formation of steady state galactic disks.
Excellent, thank you very much. So there are a couple of questions. One from Yop Shea, asking, almost stating at the beginning that he's worried that the transition from variable to steady star formation is due to the very high star formation efficiency used in fire. And basically he's wondering whether it's the very high star formation efficiency that basically leads to a very strong variability if there is enough cold gas coming in. So that's basically the question. Do you think there is a link with basically?
Yeah, I can imagine this connection, but I don't see how that explains the fact that there's a transition that suddenly this variability disappears. Right. So I see how that could increase variability, but I don't see why that would explain when there's a sudden transition from variable star formation to kind of a much more steady.
I guess then he goes on in the question and says that the low redshift there could be enough, there could not be enough gas basically to populate the very high density, and so that could basically change the behavior then going forward.
Yeah, so the issue is that we see this transition at very different redshifts. So we see this transition both at low redshift in kind of the Milky Way mass halo, but also in the massive halos, we see this transition happening at a much higher redshift. Okay, so basically this transition happens close to when the halo mass crosses 10 to the 12, and it's practically independent of when at which redshift that happens. Okay, we have even one simulation of a kind of cluster size halo where this transition happens at redshift 5. So,
excellent. Thank you very much. Yeah, there are other questions coming in, but please check out the Google form for more on that. Thank you very much. So we'll now move on to the next speaker, Céline Perron, telling us about prediction on the angular dependence of gas mass flow rate and metallicity in the CGN. Thank you very much. Looking good. Thank you.
Hi, everyone. Thank you very much for giving me this opportunity to present some of our work to look at the physical properties of the CGM in particular. Let's see. So I'd like to start with this movie from TNG50 that shows how gas from the cosmic web filaments is feeding galaxies, cooling down through Lyman alpha radiation into this atomic and then molecular gas phase that will be the fuel for star formation. And then galactic, supernovae-driven and AGN-driven galactic winds will in turn be expelled from galaxy and pollute the surrounding regions, the CGM regions, with metals in particular, as shown here with the blue color scales. And this gas is moving in and out of galaxies with speeds of typically hundreds of kilometers per second. But this full Baryon cycle is not captured by H-alpha luminosity, that is the most direct tracer of stars and galaxies. This is a gas-based process that is taking place in the CGM halo, and we think plays a key role in galaxy formation. So here I'm showing one example of a galaxy in TNG50 at redshift 0.5, rotated edge-on. The left panel is showing, again, the gas metallicity, where the yellowish colors are solar metallicities, and the darker colors are a 10th solar. And I'd like to define this azimuthal angle, which is essentially the angle between the major axis of a galaxy and its minor axis. And you see from that one example, this is a halo with a stellar mass of 10 to the 3 solar masses, that the metals distribution about the galaxy is very uneven. And in fact, there is evidence of more metal enriched along the minor axis of the object. Now, the right panel is showing the gas radial velocity, where red colors indicate outflowing gas and green colors, gas that is falling onto the object. And very qualitatively, you can see there's a match between which way the gas is going and its metal enrichment. Now, how does it show statistically? So here I'm showing a measure of the gas mass flow rates in solar masses per year per star radiant as a function of this azimuthal angle. So again, low azimuthal angle is the major axis, and along the minor axis, the azimuthal angle is 90 degrees. And this is telling us at an impact parameter of 100 kiloparsec how much in a shell, if you want, around those 100 or 500 galaxies, how much gas is moving in and out, right? And I'm showing this for two major simulations in green and purple. This is results from Eagle for 2 stellar mass ranges. And in blue colors are results from TNG50 for galaxy with stellar masses of 10 to the 10.5. And what we see here is, despite very different numerical and physical processes in both the simulations, there is a trend of mass of gas moving in along the major axis, and most of the mass moving out along the minor axis as a net result of those processes. Now, the question is, can we probe this with observations? As you know, we've been, like many groups, combining both quasar observers as tracer of the CGM gas with galaxy properties as probed from detecting galaxy near the observers, in particular using 3D spectroscopy. And this right panel now shows measurement of these gas mass flow rates in both Symphony and Muse observations of magnesium-2 gas. Now, I have a few points that I'd like to make about this plot. One is that by construction, the observer defines what's inflowing and outflowing according to this azimuthal angle definition. So somehow in this plot, the y-axis is a define of this reasoning. The second point I'd like to make is this is a very difficult quantity to measure in observation because, first of all, this is a derivative of time, so it's intrinsically difficult to measure at a given moment. It has a number of assumptions on the H1 column in particular, and it's also model dependent when it has to assume something about the opening angle of the gas inflowing or outflowing. And thirdly, as I said, these observations are based on magnesium-2 observers, which are probably tracing gas around 10 to the 4 Kelvin, while the left plot is showing all the gas in all its phases in those simulations. But nonetheless, I just want to have those two plots side by side, just as a hint, that perhaps we can hope to look at these quantities in the somewhat not too far future. Perhaps a more direct observable could be to look at the metallicity of that gas. So I'm showing here in another sample of TNG50 galaxies, there are about 70 objects here. I'm showing the gas metallicity on the x-axis as a function of the radial velocity of a gas on the y-axis, where the black solid line at radial velocity of 0 indicates that to the left, the gas is moving in, and to the right, the gas is moving out. And the color coding is with azimuthal angle. So what we see here is this typical gamma shape where the gas that is moving in galaxy is more metal poor. It has lower azimuthal angle, while the gas that is moving out of galaxies is enriched by star formation processes within the galaxies, and it's flowing out along the minor axis of a galaxy. So here, how we summarize these results. This is the main plot from this work, again showing the gas metallicity as a function of azimuthal angle for the two simulations, TNG50 and Eagle, showing that, again, despite the complexity that was shown in the movie I started with, where gas is falling in and moving out, but perhaps falling back onto galaxies, the net result is that there is indication that the metallicity of galaxy, of the CGM gas around galaxy, is a function of the azimuthal angle. And Enrique has highlighted how these results are even enhanced when magnetic fields are specifically taken into account. So how does this change with impact parameter? There is actually a stronger strand at a B of around 100 kPa, probably because this is at a distance where the fountains have not yet completely mixed the gas, which may happen even further down. This signal we find is a strong function of stellar masses. And this is expected. I mean, essentially, this is related to the mass metallicity relation of galaxies. But it's an important point because it means that observation would have to select samples of well-known stellar mass ranges to uncover this signal. And I'd like to stress that this is not an effect of the chosen impact parameter because it's also true at fixed physical scales. So I'm showing here the same version of a plot, but at a fixed halo radius, if you want. There is indication of evolution of a trend with redshift. So again, you expect increasing metallicity with cosmic time as stars are being formed, and in fact, it's at lower redshifts that this trend is expected to be the strongest. And we have looked how a column density in H1 cut affect this relation between gas metallicity and azimuthal angle, and it's shown here for different NH1 cuts. And it indicates that the trends remain, but the significance lowers. So that implies that more observations of the same kind would be needed to recover this signal in H1 gas, in H1 selected gas. So what are the current observations? Here we've been very picky in selecting metallicity measurements that are based on non-H1, but also that are based on metallicity indicators that are corrected from dust depletion. So typically, using zinc over H as a metallicity measurement. And I'm showing the very few data points that are currently available where both metallicity in the gas and azimuthal angle has been allowed. And I'm also showing that half of this sample only has stellar masses measured, and they are ranging from 9.1 to 10.7. So I'm making again the point that we would need a very specifically selected sample to uncover the signals that the simulations are predicting. I'd like to highlight the recent work from Martin Wendt and collaborators that has looked at the dust depletion as a function of azimuthal angle, which can be thought of as a proxy for metallicity. And they seem to find already in their Muse observations a trend of dust depletion with azimuthal angle, as we would expect go higher with higher metallicities. So to answer the question of this conference, I think there are been a lot of data coming in, a lot of simulation with increased resolution that are helping us understand some phase of a CGM gas at least. But I do expect there will be more to come, because as been hinted already in some of this conversation we had, I think there are one step further to go for simulations to go to the scales, but also to the physical processes and the phases of a gas that we are observing that have not yet been simulated fully in a cosmological context. And on the other hand, I believe that we need to gather large samples with well-controlled physical, galaxy physical properties, including stellar mass, which are not, unfortunately, part of IFU observation, but may require, HST and broadband imaging in addition to the IFU observations. So as take-home messages, I'd like to report that both TNG50 and Eagle predict a trend of CGM metallicity with azimuthal angle. We think that 3D observations of a large sample of well-controlled galaxy absorber pairs would uncover this signal. And globally, I think probing the mass, the metals, and the energy budget is very important for our understanding of the cosmic baryon cycle. And I'd be happy to take questions.
Thank you very much. Thank you for a very nice talk. There are a couple of questions. We'll probably have time to take one while the next speaker is setting up. So it's a question for you, Celine, but there is also a reference to Dylan. And the question is from Zach Haffen, asking whether there is evidence or a reason to suspect that the azimuthal dependence of the CGM properties extend below the yellow mass regime where black hole feedback is expected to be important. And I guess he's online, you can chime in and comment on that if you want.
Yeah, I mean, that's a good point. So I've shown, and sorry, I have unshared now, but I've shown that we looked at how this trend that we're observing is a function of stellar mass. Obviously, only the higher stellar mass will have AGN-driven outflows. And indeed, in those objects, which are very few in TNG50, there is another property that may take into account. But most of the objects I've been talking about at somewhat lower, stellar mass, where most of these galactic winds are supernovae driven.
Excellent, thank you very much. There are probably other questions, but we'll move them to the Google Doc, so please go and check it out. We'll now move to the next speaker, Zachary Hafen, talking about from observation to dynamics and disentangling gas flows in the CGN. Thank you very much.
Great, thank you. Can you hear me all right?
Yeah, we can hear you. Yeah, now I can see the presentation.
Okay, great.
Yeah, take it away.
Okay, so I have changed my title and talk a little bit to better suit the conference question, and also to do so while making sure to be within the time limits given. And so I will be just trying to directly give my input instead on, is the study of the CGN revealing the processes that drive galaxy formation? And as just a brief punchline, the answer I would say is yes, absolutely. But more particularly, in order to reveal the primary processes that drive galaxy formation, we need to perform a comprehensive analysis of all the components of the baryon cycle. I'll get into both of these two in detail. Okay, so first, let's just take a look at one particular process that drives galaxy formation. And just by answering yes to even any given process, then we have already said that the CGM is important. So I'll be focusing on quiet accretion. This is a CGM process that drives galaxy disk formation. And I have a visual on the right-hand side of 3 trajectories drawn from a simulation, from the fire simulations, in fact, for gas that undergoes this quiet accretion process. And quiet accretion is characterized by 3 different attributes. One is it's hot throughout the halo. You can see the color of these trajectories as they move inwards closer to the galaxy is close to the virial temperature of the galaxy. And for this is a Milky Way mass halo. 2, it cools once it reaches the galaxy halo interface. And then as it cools, it aligns itself with the galaxy prior to accreting. So this is the so-called quiet accretion that, for example, Putman et al. Have discussed in the past in, for example, her review article in 2012. And the key conditions for this to occur are that the halo needs to have an inflowing, stable, hot, virialized, volume-filling component. If these conditions are met, then we have reason to believe that the mechanics for quiet accretion will proceed. And as a case study, I'm going to look really quickly at Milky Way mass halos at redshift of 0. So this is some work that I'm doing with Jonathan and James Bullock et al., as well as other members of the FIRE collaboration. And what we do is we perform a detailed trajectory and property analysis of gas before and after it cools, prior to entering the galaxy, as well as tracking a little bit past when it enters the galaxy. And so what I'm going to be showing on the right are a series of plots relative to the time at which the gas cools, left before cooling, right after cooling. So let's go and zoom into each of these bit by bit. So the top panel, we have the gas moving in, showing the radius as a function of impact parameter. The solid line is the median for all tracked gas. The sample is gas that was in the galaxy at redshift 0 and outside the Milky Way mass halo 1 gig year prior. And you'll see that it's moving inwards as part of this cooling flow. If you take a look at the rate at which it's moving inwards, it matches the speed of a cooling flow. But then after cooling, it stalls. And of course, it cools at the interface first. And you can see that by the matching up of the change in slope and also the line at the t equals 0 time and close to the stellar end of the stellar radius of the galaxy. So why does it stall? Well, to understand that, we'll go down to the next plot. So moving inwards, the gas is not fully rotationally supported. This here shows the angular momentum magnitude divided by the magnitude of angular momentum necessary for full rotational support. And then on the right-hand side, as time goes on, gas reaches full rotational support and thus stalls. So that's why the gas stops and stalls. Now, that's not the full picture. Why does it align with the galaxy? Well, here we can see the JZ component of each individual gas particle relative to the angular momentum magnitude of the gas particle. And what you'll see is that as the gas moves inwards, this width of the shaded region, which shows how much scatter there is in angular momentum, decreases. Basically, the gas becomes more coherent. So this is because the volume filling hot halo enables exchange of angular momentum. And eventually we reach the point where the accretion is fully aligned with the galaxy. And that makes it very conducive to disk formation. And therefore, what we say drives some level of disk formation in galaxies. Now, the last piece of this puzzle that's missing is, why does the gas cool? Well, first, it stays hot during the infall because cooling balances heating. So here we have the two main energy terms for this gas. One is radiative cooling. The other is heating due to the gas moving inwards and being compressed, basically doing PDV work on it. And when it reaches the galaxy halo interface, because it stalls, there is a pileup of gas that bumps up the density and therefore increases radiative cooling. At the same time, because it stalls, the gas is no longer moving inwards and compressive heating drops off, and therefore it cools rapidly. So this is just one physical process of the CGM that we have reason to believe affects galaxy formation. And therefore, definitively, yes, it's important. Now, I don't have much time left, so I'm going to go very briefly into the other part, which is that in order to look at the physical process that drive galaxy formation, we need to think of galaxies, the CGM, intergalactic medium, and satellite galaxies as part of a system. All these different components interact with each other. And this is a huge challenge because each of them individually is very difficult to understand. But in order to understand the system as a whole, in order to understand how central galaxies depend upon the CGM, it's important to recognize the environment which they're in. So I have more information on this. If you'd like to talk to me, I'd be happy to answer your questions. Otherwise, I think I'm about out of time. Is that correct? Okay.
Great on time. Thank you. Thank you. Is there any question? Come in as everybody maybe sets up. Okay, maybe I'll ask a quick one. So I guess you emphasize this idea of all the components of the baryon cycle. So that's kind of very challenging for observers. And so I know you probably don't want to answer this, but where should we focus our attention first, rather than getting all of them in one go?
So I think there's two regions that are really important for focusing on first. The first is identifying particular processes that we believe are really important to galaxy formation. So I like to believe that quiet accretion is one such process because it will potentially be very important for disk formation. And so from the theoretical side, we want to identify some of the most important processes, some of the most important channels in the baryonic cycle. Now, then we also should complement that with understanding from the observational side. We should also try and understand which channels of the baryon cycle are most visible in observations. For example, many cosmological simulations are now coming to the consensus that cool gas in the outer halo of Milky Way mass halos is oftentimes associated either with satellite galaxies or perturbations from the satellite galaxies. That means this cool gas is very highly visible oftentimes in the CGM. But whether or not it actually affects the galaxy formation of the central galaxy is another issue.
Excellent. Thank you very much. Appreciate it. Thank you for a very nice talk. There is a question coming in, so maybe check out the Google Doc. And we'll now move to our last speaker for today, Avery Maxing, who will talk us about metal absorption system at the end of ionization.
Hi, can you hear me? All right.
Yeah, all is fine. Thank you.
All right. Well, I'd like to thank the organizers for organizing this specialist meeting and for giving me a chance to talk about some recent work. This is work involving quite a few other people. Let me try to step through that. Right, there we go. All right, so I'll try to answer the question of this meeting, talking primarily about a paper of modeling low ionization metal absorption systems at high redshifts near the epoch of reionization. This is work that was done primarily by Teresita Suarez Noguez. She is unable to present the work herself because she's on maternity leave, so I'm presenting it for her, but it's both of our work. And I'll talk a little bit about some simulations as well, where I hope there's time for that. All right, so what we've done is we're looking at these low metal ion systems, which are probably coming from damped Lyman alpha and subdamped Lyman alpha systems. The results are consistent with that, and that's what was surmised by the observers. As a means of trying to understand what are the nature of the galaxies that these systems are associated with and where they came from. Because these systems are believed to be quite small, meaning hundreds of parsecs or even smaller, we use pressure confined models. And we assume a radiative background using the Hart-Medal spectrum. We actually consider 2 models for their spectrum, but most of the results are from the 2012 model. And we model the radiative transfer using Cloudy, but we do some things a little bit different from what's usually done. Usually, so Cloudy really only does, in the context for the CGM or IGM, slab models. And these slab models are only approximation to what we think are probably more spheroidal systems. So what we've done is to mathematically transform the slabs into cylinders. We can't do it into spheres because that doesn't work, but into cylinders in order to have lines of sight that are passing through edges of a cloud rather than always through the center. If you just do a slab model, you're effectively only passing lines of sight through the center of a cloud, looking at the core. But some lines of sight won't pass through the core. In fact, most won't. And so that's the kind of effect we also want to include in our models. And so when we do that, I'll just give some highlights from the papers. This paper you can now see, it's now been published recently. But this is just a few highlights. So here we're looking at the ratio of column densities of silicon-2 to oxygen-1 coming from observations, mostly from Becker, also from Valentina and Cooper and Bañados. And what we find is that, well, if we were to do a slab model, the model points are these colored points without the error bars. The slab models will be concentrated near the centers here. This one is for solar abundances, the other is for starburst abundance. Alpha enhanced abundances. And by rolling the slab into a cylinder and allowing for peripheral lines of sight, we could actually spread out the kinds of column densities you would expect. And what we're finding is that the observations, and Teresita's done quite a comprehensive analysis of the literature. This is just a small sample of that. And what we find actually is that the data fall pretty much between these 2 models, which suggests that the abundances of these absorption systems lie somewhere between starbursts and solar abundances. But I will notice that we find that there's a number of systems that show silicon to oxygen ratios that are anomalously low. And these aren't fit by the models directly, but they are consistent with dust depletion, a moderate amount of dust depletion onto dust grains. And so what it suggests is that these absorption systems are actually exhibiting a rather advanced ISM structure, showing, in fact, possibly the presence of dust. I'd like to point out it is important in interpreting these data to look at the subsystems. So many of these absorption systems show quite a lot of velocity substructure. And that's not actually usually reported by the observers, but it would be really helpful if those were separately fit. It has been done in a couple of papers by Pudel. This is just an illustration of what happens when we do that. So I hope you can see my cursor, but if you look at the small cross that's near the bottom of the solar range of points, I should have mentioned these points allow for different densities of the clouds, and so different pressures, but all pressure confined. If you took at that small cross, that's a combined system. If you look at the subsystems, it separates into the two golden crosses. And what we see happening is that a system that looked like it was near the solar line of sight passing near the center of the cloud actually separates into two systems with lines of sight passing through the periphery of the cloud of solar abundance, and another one showing perhaps silicon depleted system with starburst abundances, right? And so the interpretation of the subsystems can be rather different from the combined systems. And that's why it's important to actually look at these subsystems as well. We did do a little exercise to see if we could infer something about the background. Since we're looking at low metallicity systems, the UV background isn't so directly probed, and we did some experiments with that that show that the results aren't very sensitive to small changes, even a factor of few changes in the UV background. But if we do a large change, as in the Pukvine model at a redshift of around 6 or 7, that model has quasars dominating the UV background to rather higher redshifts than the Hart-Medal models. And that results in actually really low ionization background for hydrogen at these high redshifts. And that results in actually, if we look at the iron to carbon ratios and silicon to the carbon ratios, to a very localized region in this space of column density ratios. Whereas if we'd use the Hart-Medal model, it would actually embrace the Bañados point here. We can see the purple point, and it stretches out into where these points are occupied. And so it does actually suggest that this low ionization background model is not favored, but we really need better data to really probe that. Okay, I'd like to move on a little bit and talk about the origin of some metal systems. I'll just concentrate. This is a project done, most of the work was done by Kimi Fujita in Japan, with several collaborators listed here. Here we looked at a dwarf galaxy motivated by the idea that what we might be seeing are metals that aren't associated with the bright galaxies that we see nearby, but actually with dwarf galaxies that are too hard that have been too low surface brightness to have imaged yet. And we look at the winds that could expand. We do a model where we allow for a starburst, a single starburst we want to follow, and we allow for luminosities and energy input and mass input coming first from type 2 supernovae for 40 million years, followed by a phase of type 1a supernovae. This is just to show that at the end of the type 2 phase, we develop a classic superbubble structure. If we look at the middle diagram, the greenish region is showing fast outflowing gas. The purple region is above that is showing the gas is slowed down, and the red region is actually stagnant shell going around. And this is a classic bubble structure as described in the 70s by McRae and Mordecai McLeod.
1 minute, please.
All right, and now what we do is turn on the type 1a supernovae. These aren't weaker, but they last for a long time. So if we wait 160 million years later, we find that we get a very complex structure, and we're just going to concentrate on this interface region between the fast and the slow region in terms of length scale. And if we look at the top panel, we're seeing the density structure. We're also seeing it at different resolutions. So if we concentrate on the middle column, on the middle column, then we can see that there's a rather complex density structure. If we look at that, the box enclosed in blue, we find that as actually region where the type 2 supernova material is now cooled and is falling back in, and it's meeting the outflowing supernova 1a driven material at a shock front. That cooled material is now cooled to even lower temperatures and results in the formation of low column density magnesium 2 systems, which is shown in the middle panel. It's the magnesium 2 density. We can see that it's quite resolution dependent. If we look at 25 parsec resolution on the right, and 12 parsec resolution in the middle, and 6 parsec resolution on the left, we find that at 12 parsecs, it's not too badly resolved, but 25 parsecs isn't enough. On the other hand, we see the column density and covering fractions aren't very sensitive to that, but the velocity structure may well be. And that's the reason for looking at the velocity structure at high resolution. And so in conclusion, I'd just like to say that I believe that we are learning about the galaxy formation, galaxy evolution from the CGM studies. This is just a taste of what we might be learning. So for example, it does look like these low ionization damp Lyman alpha and subdamp Lyman alpha systems are coming for telling us something about the galaxy formation process that's coming from material that's somewhere between starburst and solar values. And we also find, as others have found, that the CGM is a very complex arena of outflows and inflows. And in fact, the origins of some of these systems may not be clouds propelled from the ISM of a galaxy, but could be forming in situ through the collisions of shocks driven by supernovae from those galaxies. Okay, so I'd say still we have a long way to go to unraveling what the CGM is telling us.
Thank you very much. We have time for a quick question, if there is one coming in.
Okay, you read them, Michele, because I can't see them easily.
Sorry, what?
I can't see them. Or maybe
Yeah, no. I'm waiting for them to come in. Yeah, I think there is one from Max Gronke asking if you can.
Mass transfer rate.
Yeah, you said. So basically, it's asking whether you can comment on the mass transfer rate between the hot and the cold phase as a function of radius in your outflow model. For example, do you not see any cold gas run pressure accelerated or via momentum transfer due to mixing?
I suppose it's in there, but it's not. We haven't done a specific analysis to look for that effect. The gas itself is really quite mixed, as you could see. It's not so easy to isolate the cold. I mean, we can isolate cold and hot phases. We do have plots that show the temperature. Well, here it's early on. We do have other plots that show the temperature later, and you can see what mixing is going on. And there is, in fact, part of what we were interested in is to see if we could actually see mixing layers. And it didn't look like that was really a driving factor for changing column densities. But the cold and hot gas are mixing, but you also are forming cold gas. It's not quite so easy to actually follow cold gas when you're generating cold gas in the shock fronts as well. All right, but that's
excellent. Thank you very much. I appreciate it. Thank you for a very nice talk. I'll now give it back to Emma and Matteo for some of the discussion and more interactive polling, I guess.
Yeah. So firstly, thank you to all our talkers, both this morning and this afternoon. They were very interesting talks, I think. And we've got about 15-20 minutes before we have to finish up for the RAS ordinary meeting. So we wanted to kind of open the floor and have a bit of discussion, a bit of engagement going. So if you do have any kind of comments, any questions, please raise your hand and one of us will give you the ability to speak. But as Michele said, a bit more polling, try and get the views of kind of everyone who's watching, the kind of overall community. So if you go back to the link I gave you earlier, so this is aharslides.com/RASCGM. If everything's working well, you should now see a slightly different question. So now we're asking, what's the best statement that describes the current status of the field? So I will give you a couple of minutes. I can see people logging on. But while that's happening, I can share the screen and show you the results from this morning, because we had a couple more results come in. Okay, can you see this okay? Yeah.
Yes, we do.
Yep, so here's the link if you've lost it. So I think after we started talking, there were quite a few more votes for I don't know. So about a third of us weren't quite sure. I think at the end, we'll poll you again on this question and see if maybe the talks today have helped a bit, whether there's a bit more yes, no, or whether everyone is still just as unsure. Personally, I think the talks were quite positive, quite optimistic. Well done to everyone who kind of stepped up to the challenge of publicly stating their opinion during their talk. And I think most, or a lot of people were saying that while we've got a lot to do still, actually, yes, we are making progress, and yes, this kind of effort that we're putting into this area of research is actually quite productive. And on that topic, I will share the screen to show you the results that are coming in now for this next question, which I think is quite interesting.
You can also find the link in the chat if you lost it early on. So if you go in your chat window, you should also find the link.
And on the question from Martina of how many people were attending on average, this morning it was about 50. Of course, we've now dropped to about 40 now. And so far, as I show you this, so we have 20 people have now voted. If I can look this. 20 people have voted, so we've still got another 15 or so people who give their opinion. But I don't know if anyone else has any comments they want to say, but this looks pretty good going to me, that we're making good progress.
Then if anyone wants to make, go ahead, Matthew.
No, I was about to say it's probably positive that nobody said we're almost done. Otherwise, we don't have anything to do for the future. And it looks like the numbers are quite low in terms of, so there is no consensus in terms of whether we should make our effort more on the theory or on the observations. But as more votes come in, this might change.
We're getting a complaint from Max Kroenke, was saying that it's a biased crowd. So there is a little bit of bias in the distribution and so in the voting. But if we correct for the bias, I think we'll get
say if there's an option that's, or what you want to say is not here, then please raise your hand and let us know what you'd like to say.
So we have a raised hand from Celine. Okay.
Yeah, you should be able to now talk, Celine.
Yeah, hi. I guess I was going to add up on what Max is saying, right? I mean, perhaps the answer to this question would be, slightly oriented. So let me ask back, why was the question posed by the organizer of this discussion session? What is, the reason why you seem to think it's a good question to ask?
So I guess in some sense we are being a little controversial. I think it's generally quite good to kind of take a step back and look at the bigger picture sometimes. That's not necessarily us saying we don't think we're lacking, we're not doing stuff right. I think we are doing quite a good job. But I think this kind of discussion meeting is a good opportunity to kind of take stock of where we are.
Yeah, I see your point. So perhaps, and I think the question has been answered, or even asked. Perhaps we could refine the question, which is, what do we think theory needs to advance upon, and what do we think are the observables that we would like to gather?
That is a brilliant question. So if everyone who is on that link, I can now ask you that exact question. So seeing as theory had 4 votes, we'll go for this. Okay, what's missing the most in simulations to fulfill the promise?
Avery and Max raised their hands, so
I mean, I was I think sorry, this is Max. Oh, sorry, should I speak or not?
Max, go ahead, and then we move to Avery.
Thanks a lot. Sorry. I was saying that I think I don't think we've seen any simulation or theory work here, right, where we have sufficient resolution and the physics included that's really needed, right? I mean, we know magnetic fields, cosmic rays, they're very important. They're depending on very small scale effects in order to compare to observations. Thermal conduction is important, right? I think there's I voted for theories lagging way behind, and I mean I'm always amazed seeing all these observational progress, and I think the theory is really way behind what for the CGM at least.
Thanks. Now we can have Avery.
Right. Yes. Well, observationally, I'd like to see more high-resolution spectra done to understand the kinematics better of the CGM, the substructure of systems. But also, radio observations in the future can tell us a lot more about the role of magnetic fields. I'd like to see. It would be great to look at the eye of the galaxies nearby, but that seems really difficult to do. What I'd like to do is ask an even broader question. What are we hoping to learn from simulations and their comparison with the observations? Do we just want to match the observations, or do we want to understand? I'm interested in understanding the physical mechanisms that are driving the wind, and that's actually quite difficult for simulations to do. So we start out by having more gross approximations for the wind generation process and see how that matches the observations. But ultimately, what do we want to learn about? I think we want to understand the types of winds that are forming actually within the ISM of the galaxies and the physical conditions and properties that give rise to the wind. There's still unknown questions like how much mass loading, where's the mass loading coming from, what is the rule of thermal evaporation in the wind bubbles, and those are topics that are still quite some distance away, I think, from simulations being able to answer.
Yeah, thank you. I think Jonathan has asked to make a comment which might be very similar to what Avery was saying.
Not exactly. So I'm the second one who said that this theory lags behind observations. Yeah. And I think the simulations are amazing, but we lag behind in our ability to understand them. So I think even in the relatively simple simulations, which don't have all these fancy physics like magnetic fields and cosmic rays, we still don't have a good intuitive understanding of what is happening and what are the main kind of mechanisms governing the CGM. So I think you're missing in this question. I think we're missing another question, another column, which says we need to better understand the simulations before, or maybe instead of adding more complexities like additional physics. So even the relatively simple processes of hydrodynamics and cooling and stellar feedback and relatively simple processes, I think we still do not have yet a good understanding or a good intuitive understanding of how they work.
Thank you, Jonathan. Also, Valentina asked to make a comment, and then also Joop.
Yeah, so I was wondering, and this is a question to simulators, if increasing the resolution, let's say, to better resolve the CGM is kind of opening a Pandora box, in the sense that then we need also to improve, for example, some physics that now is, so grid and maybe just put with very simple recipes. And then instead, if that resolution is increased, we should put more realistic. I don't know if this is a problem.
Joop, maybe you want to answer that?
I first want to say that we are going to get a flood of new observations, very exciting data from all kinds of things. So this field will remain observationally driven. Then on the simulation side, now, of course, to do the ultimate simulation, you need all the physics, all the resolution. But what I tried to mention also in my talk is that we should be a little bit careful not to think that all that is necessary. The Galaxy simulation community went through this, that for a long time, no simulation could make a reasonable galaxy. And people were coming up with, of course not, because you don't have cosmic rays. Of course not, because you don't have parsec resolution, whatever. Turned out to be, you just need to have one single feedback loop, doesn't matter which one, and make sure you don't numerically overcool, and then you get galaxies that look reasonable. So not everything that exists in the universe will be important for, and And it can be counterproductive to add all kinds of new physics in there that is unconstrained. And and of course, these need to be studied as well. But there echoes Jonathan as well, that we also have to understand better just the simple physics. And just throwing everything in there that we know exists can be counterproductive.
Yeah, I personally agree. Now, Tristenberg is asked to make a comment.
Yes, I just wanted to follow up something Valentina said in her talk. I think also including a better kind of physics for the metal production in simulations. Even getting at detailed chemical abundances, for example, can tell us some things about how some of the metals are getting out. But again, this is adding another dimension that may be too complicated. But it's something I think could be very interesting, like looking at this carbon to oxygen ratio, for example. That kind of gives you both a nucleosynthetic component, but also telling you something about supernova versus AGB contribution to your gas. So yeah, that's all I wanted to add.
Okay, I'm just quickly going to share the opposing question. So we just looked at the what's missing in the simulations. What is also missing in the observations. So again, if you go to the same link, you should now see this question, what's missing in the observations to fulfill the promise. I can see lots of hands up, and I'm very sorry that we're not going to have time to hear from everyone. We have to stop in 1 minute. So I think what I propose is I will put up the overarching question, as I said, so is the Cgn fulfilling its promise? It'd be interesting to see what everyone thinks again now. And then I'm going to put all the results onto the Google Doc, so you'll see these bar charts. So if you do want to say anything, please feel free to add some more comments in on there, and we should all be able to see it. Quite interesting if you can see the results coming on for the I will give it just a minute more, and then I will change the question one final time. I think we're okay. Okay.
I guess on this one, we all seem to agree that I guess multivariate observation really covering emission and absorption are really what we want. And as Job said, we're, I think, heading towards a really happy period for this, because we'll have really lots of new observation coming in. And so that will, I think, provide really a lot of observational constraints we can use to go back to some of the questions we were posing on the simulations as well.
Okay, so there you go. You should now see that final question. I want to say thank you to everyone for coming. It's been a great meeting from my view, and lots of interesting science. And hopefully in a year or two, we'll be able to come back and do something like this again.
I just want to use the last second to just really thank Emma for all the hard work she has done, and Matteo as well. I think they did a great job to put together this meeting. Despite these difficult times, we have now also the leisure to think about happy things like science, and we thank them for their hard work to put us together and spend a good day talking about CGN. So I think on behalf of everyone, I'm just gonna thank them for this very nice meeting. Thank you.
Thank you. Bye.
Thank you.
Bye-bye. Thank you.
Bye.
Thanks.